you. Right, before we go any further, I'd like to do a selfie. It's always good.
Oh.
Oh, okay. Okay, we go. You're welcome. That's cool. Thank you very much. It's always good to get those bits out of the way first. So, greetings. I'm going to have to work out how I actually stabilise myself now as we go. It's great to be with you. So, for those of you that don't know me, there's probably one or two around. So I think this is my 33rd IBC. I calculated. Wow. I did the very last one in the UK in Brighton, which I think was 1991. So that just shows I must have been 5 when I started coming, I think. Anyway, so I was with BT for a long time, and then basically kind of Norwegian companies that do broadcast stuff, and I've been with a peer almost just coming up to 2 years, so very excited to be here. I thought what I'd do is, seeing as we're getting going, I'd do a little bit of reminiscing just for 3 or 4 minutes to get a. Can you see? Okay. Okay. To give you some context to what I think is quite a sea change in the way we're going to be doing live production moving forward. So I thought 100 years of television is quite astounding when you think of it. And there's been lots of changes. There's been massive changes in the way people consume television. You know, linear television, as we have known it for almost 100 years in some form or other, is definitely on the demise. And also, very importantly for this talk and this show, the way we produce television is changing just so radically as well. This is a picture I've shown many times. I think it's a really good one. This is getting back to the production side. Location agnostic live production. This is a slide that the DPP came up with. Actually, during COVID, we brainstormed this. And for those of you that can't read, basically it's talking about the different models for how we actually do production now. This top model, where the acquisition devices, the cameras and microphones, the processing and storage, or VTRs or whatever they used to be in the day, and all the controls were all co-located in one case. You know, you had your studio floor and your gallery, or you had your OB truck of whatever vintage it was, and you did that. But all of these other models now apply, where the acquisition can be differently located to the processing and storage, which can be differently located to where people are controlling it from. And that's the flexibility that IP infrastructure has given us, and we're leveraging that, and we're seeing certainly quite transformationally many people doing, especially now, more centralized production. That seems to be where people are heading in terms of the way that production is done. Also, general context, I've used this slide a few times in the last year. We're moving from the bespoke to the generic, which is a good thing. For those of you that have fought with the eye diagram on an SDI or an HD SDI, or unbelievably a 12 gig SDI signal, then we're abstracting ourselves from the physical layer now. We just have Ethernet connectivity. Similarly, a lot of the infrastructure we do is now not on bespoke devices, but it can be housed on compute, which is generic, and there's all sorts of advantages in that, and obviously a few challenges as well. And networking as well. Networking, especially for live production, was the preserve of highly expensive private lease lines. Now it's amazing how much networking we're actually using. A lot of customers are using what I call best efforts, internet connectivity. I mean, internet connectivity is massively better than it used to be, but still we're actually able to use that technology to actually run it. Another observation, compute is genuinely ready for real-time uncompressed video stuff. So, we've actually got the coming together of quite a few things. So we've been talking for a long time about the broadcast industry needing to leverage the IT industry because it's massively bigger, everything from the Ethernet interfaces, the infrastructure, etc. And the best principles as well, including security, just plugging in there. We need to learn from the bigger IT industry on that. But we actually have the ability with 100 gig interfaces are now quite ubiquitous, and we can actually do a massive amount of uncompressed video transfer through there. And similarly within the compute devices themselves, be that the bus transfer, the speed of I/O between the devices, etc. So compute is ready for that. Now about computers. Computers don't work natively like we're used to it with the linear stuff that we've been doing television with for a long time. So I've got this I've got this diagram here. So we're used to a linear flow of data. And what we're actually moving to in the middle here as an inevitable trend is what I've called here, if you can't read, non-linear time-aware software processing chain. So basically, we've got compute in the middle, which hopefully, and I'm going to unpack this in a minute, we let behave natively and optimally as compute. And then at some point from the camera inwards, and it may end up being on the camera itself in the future, we move from this linear acquisition that we've got, you know, the frame rate or the audio sample rate we're capturing the audio with, through to an asynchronous transfer of that data. And I'm going to unpack that a little bit later on. The other benefit of moving to compute for the live production processing workflow is all of those other stuff that was the preserve of post-production and offline stuff suddenly actually can become integrated. So a lot of the tools that would have been offline processes actually can become part of the workflow, and there's some other initiatives I'm going to mention that actually allow that. So in the beginning, so this is, again, hopefully some of you can see this very mechanical scanning. This is one of the earliest television devices, and the reason I wanted to show that is right up until including 2110, which is, I guess, the latest IP digital standard that we're all knowing and loving, or hopefully mainly loving, of the last few years. We have inherited the legacy of the raster scan. So we have still got, I can actually hear a delay on my voice coming back from somewhere. We accommodated within 702110 the flyback time for the horizontal and vertical blanking, even though we were trying to start again. And that's because we've preserved this concept of linear stuff. Is there any chance of turning the volume down? That would be great. So what we've had even up to 2110, and we've got some lessons to learn from 2110, which I'm going to talk about in a minute as we talk about this hybrid workflow. We have this completely linear thinking, right from analog video through to and including SDI, various variants into 2110. So when I've got a little analogy here, I always like to have a little analogy. This is one of my grandchildren holding a hose pipe in the garden. And what I like to think of in the linear video that we've done for the last 95 years is it's a continual flow of water, or a continual flow of video information and audio information that goes alongside it. The way computers work is they like to get a bucket of stuff, do some math, and throw it back out again. They're not very good. They're not optimally set up for receiving continual small increments of data and doing stuff. And in fact, in 2110, we spent a lot of time forcing computers to behave in a linear hosepipe manner and actually very carefully spew out the data through the network interface cards, etc. Whereas they want to behave like buckets. Now, you can obviously transfer the same amount of water if you have enough buckets running it, but buckets can actually run, you can actually get a lot of water out instantaneously from a bucket. And that was one of the challenges we had with compute originally in 2110, is it would suddenly throw a lot of data out. And in a fragile UDP world on switch fabrics, it wasn't very good for that, so we had to constrain things. But actually, we need to move to an architecture where we let the computers behave with these buckets of numbers and actually do what they do well, and then we start and end with the linear stuff at the camera and at the viewing device. And actually, I guess the end game here is, the only thing that needs to be linear in this workflow is the acquisition devices themselves and the viewing devices. Obviously, there are some viewing devices in the middle that the production team need to actually view part way through. But apart from that, you can see the picture really well when we go into tunnels, can't you? So what we've got, this is 2025, so I've done a timeline from 1936, which I think is a reasonable approximation of when we really started doing television, all the way through. So we've got all of the analog stuff, all of the SDI stuff, all of the 2022-6 and TRO3 and 4 and 2110. And we get to this point here, so linear analog, linear digital, linear IP, and then asynchronous IP. And that's where we're at this year. So many of you will have heard lots of talk about MXL. I'm actually wearing an MXL badge, and I've got a thing on the back of my pass as well. And a lot of that, you can hear some more details of that unpacked on the boat this afternoon if you're coming back. But I wanted to give you a context of how that fits in, and also some of the challenges we're going to have as we move forwards, because it's not a done deal. So hardware and software processing, you're probably familiar with this, but hardware devices took a defined time to do anything. Software execution is a bit of a bell curve, and there is a maximum time you can expect your compute to do it, but it's a much more uncertain execution period. So we have to take that into account. And then obviously, if we're summing different signals from different places in compute, we actually have to wait for the worst case time of arrival for each of those processes before we can actually do the math of, say, mixing two video streams together. So that's like some fundamentals. So what we're looking at doing is, the purple is like the linear interface, and then as we hand information between software production processes within compute, we need to do this asynchronously. We don't want to have to go back to 2110 with the -21 timing model and all of the effort that takes. Not only does it take effort, it takes compute cycles to do that. It also costs time. Now, latency, as many of you know, is a pet topic of mine, and one of the things that has been really bad about latency in broadcast as we've evolved from SDI into 2110 and IP in general is we've made latency a lot worse. So whereas by the time we got to the end of the SDI generation, a really good spec vision mixer from someone like Grass or Sony or whatever probably only had 3 or 4 or 5 lines of video latency, so like a couple of hundred microseconds. Because of something called TR offset and the way we define some of SMPTE 2110, suddenly everyone got scared of actually putting something out that was just delayed by 300 or 400 microseconds. So everyone delays every part of the chain for a video frame and pushes it out on the next video frame. So every part of the process now inherently accumulates 1 frame delay. So you concatenate that. That's very, very frustrating. We don't need to do that. Added to which, a lot of software implementations actually have been very, very poor in terms of shoving lots of buffers in. Because one way to actually get rid of most problems in software implementations of real-time video is to shove loads of buffering in. You've only got to look at the way your end devices buffer stream when you view and listen to things at home. You shove a 20-second buffer in, and pretty well you can get away with anything. And so what we need to do is, because if you think about compute, each compute cycle generally is working much faster than real time. So it may be working, doing a wipe on a couple of, between 2 video sources. It can probably do the math on that in 1.5 milliseconds out of the 20 millisecond frame that you've got. So that data is ready then. Now in the 2110 world, we would actually sit there and wait for 18.5 milliseconds and then make that available. But actually in this compute world, we can actually say as soon as that data is ready, we can make it available asynchronously to the next place, and that situation can ripple down. So actually the cumulative latency only needs to be as long as the next data set is ready for the next processing. So actually this can be vastly quicker, even than it used to be in the SDI world, because we still had to do some manipulation there as well. So the time that we're taking then is, we've got this like T0 plus X, which is the time from acquisition to the point it enters the compute. And then we've got like the worst case aggregated time of these asynchronous processes. So we talked about that bell curve. So we need to accumulate the worst case processing time of all of those concatenated functions. So say we've got 5 functions that take, each take a worst case of 8 milliseconds. Then we've got 40 milliseconds worth of latency. So we can then reconstruct, if we need to, linear time at the end, and give it a bit of margin. So T plus 50 milliseconds here. That gives us the margin for our worst case compute cycles to do that. And we're actually less than 3 frames of delay in for going through all of those processes. So we need to get right this time. So I've talked about this. So we've got acquisition through to consumption, or through at least to the end of the production chain. And one of the things that we didn't think of, well, it was thought of, to be fair. BBC R&D, in their original proposition of TR03, actually covered this, but the industry got rid of it, was actually saying, if we're actually going to capture the stuff, the most important thing we need to do about that acquisition is keep the time of capture, the origination time. We need to keep that through the production process. Now, the reason we didn't do that properly in 2110, we did define it, but we did it by manipulating in an inappropriate way RTP timestamps, and then we didn't. Then every device in the chain was not mandated to propagate that, so we actually restamp all the way. So we lose any concept of origination time, which is very, very unfortunate. The reason we've got away with it for the last 8 years in 2110 is because of that hose pipe. Because in the hose pipe, traveling with a constant speed of water, I know that like 1 meter 20 centimeters of water behind is the next video frame, because it's a constant flow. So I can work out just by the nature of the buffer where I need to go back to the next thing. As soon as we hit native asynchronous compute, we haven't a clue what the hell's happening, because like each clump of data has no association that you can infer from the way you're transferring it, because it's all asynchronous. So what we have to do in this process is get it right and actually get timestamps, timing information from origination, or as close to origination as possible. There's going to be a few compromises there probably along the way, but as close from there as possible. We need to get that timing information, and we need to link it intrinsically and immovably with those data elements, those clumps of data, those buckets of data of the video and audio signals, etc., as they propagate the system. Now, MXL as it stands today in the prototype doesn't do this yet. And we've got some system level architectural thinking. There's also a lot of other things that we didn't get right in 2110, like other metadata that may be important from origination, like there's a whole load of camera information, or information about the way you're acquiring the vision and the audio that would be very useful downstream to know, in terms of if you're doing any conversion processes, actually knowing the information about exactly how it's captured, and that gets lost as well. So there's what we need to do as part of this asynchronous compute thing is make sure the timing model actually works systematically. And I think what we've done so far on MXL, what we did with 2110, I guess like we did with STI as well, we've focused on an interface. We're focused on that specific interface, not thinking about the end-to-end system. So I've been having some conversations with some of the other people in the industry that are looking at this during this IBC, and we're talking about doing another JTDM reference document this autumn that will actually not only define the interface, but will actually define what the end-to-end system needs to give us, so we can actually optimize latency, optimize efficiency, and optimize the ability to timing recovery, because we are still having to do manual lineup of realignment of essences downstream in productions. That just should never be necessary in today's world. We should have that time information with us to carry. So the stuff that's been leading up to where we're at the MXL, the Video Services Forum has done some great work in the last 2.5 years on the timing models, on thinking about what we need to do to get in and out of, when we say cloud here, I mean compute in general, and also this purple bit, which is specifically what MXL is becoming, this cloud to cloud, compute to compute. So this will be unpacked later today. You've probably seen the model in presentations already. The EBU did a digital media facility paper, which was published this time last year, just in time for IBC, and it's a layered concept, but one of the layers is the media exchange. And just thinking back to those, we don't need to worry about SDI interfaces or XLR audio interfaces anymore for AES3. What the idea of this is saying, if we're running on generic compute, all of this stuff below that is not something that's relevant to us. It needs to be competent and capable of doing integral data transfer within a time-bound period, but the media exchange can sit on top of that, so we don't need to worry about the fabric stuff in terms of the infrastructure, but we can define these layers, and the media exchange layer here is the bit that is becoming MXL, and we're converging some of the thinking from the industry to that. Now there's another Another piece of thinking that's been done, which actually is dovetailing in quite nicely now, is by the BBC, the TAMS, or Time Addressable Media Store. And this is a concept of actually having it's very simple, it's kind of obvious, but actually saying we're actually going to take that timestamp, that timing information, which we have now propagated and secured as being associated since acquisition, and we're going to use that to write into media storage. Now, that media storage can be used for near real-time stuff. So if you've got compute that's doing automatic highlights generation, stuff like that, as soon as that data's been fed in into this storage, that can be then available for anybody else that wants to use it, or any other AI processes, etc., and any tools that actually want to make use of that data. Now, whether or not you actually use that TAM storage as part of the live production workflow is an interesting question, because it does incur latency. I mean, it depends what the chunk size is basically that you're storing. So you've probably got a signal-centric path and a storage-centric path that you would have within a production, but that's an important side component. So I've been talking the last few months about a double hybrid future. So I think we've got a future where we need hardware infrastructure on the ground to actually get signals through from wherever the acquisition is into our production. The production, however, is definitely becoming more and more soft. And the reason it's a double hybrid is that software implementation may be hosted on your premises or close to you where you're doing the production, or actually may be hosted anywhere else. And I think what we're seeing generally as the preferred architecture is of the hybrid is actually people saying we're actually going to take our base load on-prem, and we're actually going to use public cloud to flex for events and dynamic stuff. So that's kind of the thinking of hybrid. Okay, challenges of the MXL journey. There's a few elephants in the room. I've talked about timing. We have to get that right. There's also the whole control and orchestration. If you think back to 2110, we were a bit slow off the mark with NMOS, getting that up and running. There is a danger. We're also going to be slow on the mark with this, so we really need to coalesce with an industry. And I think what we need to try and do is make sure that all of these elephants are named and put into working groups so we can actually address them as we move through this autumn and through to the spring of next year. Okay. A year for consensus and action. So I'm excited by the way the industry has come together on thinking about this asynchronous compute stuff alongside our traditional 2110 workflows. And I think this is a year where we're actually going to see, I don't think we're going to see any serious products that are actually supporting this fully this year, but next year those will be realized due to the groundwork that's actually going in this year. So there's a few demos you can see in Hall 14 on the accelerator stands for LMX and MCC. Do go and check them out. We've got some things we can show you on our stand in Hall 1, so do come and find us. And on our booth, we are doing very, very nice cups of tea. And I would like to reiterate, if you're ever in the UK, do come and check me out for a nice cup of tea in my garden as well. So thank you very much for your time. It's been great to be with you. Do we have question time?
Actually, we don't. We need to switch around anytime.
Okay.
Both turns were.
Okay. We'll do questions at the end. Yeah, I'll hang around.
So I'll get set up here.
Okay, we've got one question.
Yeah.
One question.
Okay, so for the source timing,
Yep.
when you have a vision mixer and an audio mixer, the composite of 30 different sources,
Yep.
what timing are we looking to keep from that? Because the source timing could be all over. We have to create a new one, but we need some reference back to the original metadata.
Yep.
We probably have to track to the latest one again in a linear fashion. Has that been considered?
Yeah, so I've got quite a few diagrams I've done on this very challenge. So, yeah, the timing plane of execution of a video mix or audio mix has to be the point of the latest, the timing plane of the signals that are coming in.
Essentially changing the audio and video program.
Well, as long as you know the capture time, so you've got two main things. You've got signals where you've got a capture time, and then you've got synthetic things that are playing in with an intentional time, like replay and stuff. And it's a matter of actually coding this together. It's a long conversation. We can talk more about it later.
I would love to have that conversation.
Cool.
There we go. How's
I'd
everybody?
like to welcome Ian Cook. He's one of our newer.
Cobb. Sorry.
What was that? Cobb. Oh, I'm sorry, Cook. Cobb. Ian Cobb he's a new speaker to the IP Showcase, and we're happy to have him with us today.
Thank you. How's everybody doing today? I just wanted to kind of come by. I've been working on these on IP-based video systems for over 15 years now, and I kind of want to come and share some of the lessons I've learned, some of the things that have improved, and some of the things we kind of still struggle with today. Once again, I'm Ian Cobb. I'm a IT systems architect. I come with a broadcast background, but I've always been focused on IT and networking. My job is excuse me. I work in a lot of professional sports venues and working with a lot of different organizations building high-performance media networks to bring together not only 2110 but other proprietary formats and converging everything together to build high-performance media networks for our clients. The company I work for is named Alpha Video. They're based out of Minneapolis, Minnesota. We've worked on a lot of prominent projects, a lot of sports stadiums around the country, and other fancy projects like the MSG Sphere in Las Vegas. Kind of the topics I want to cover is planning design. A big thing that I love is figuring out documentation. Documentation is a thing we still haven't. We need to communicate about how these systems work, and documentation is an important part of that. Physical fiber planning is typically very, very important with large IP deployments, and then we'll talk about a few things we've learned in the field. What is the media network? Today, you know, as we're moving forward, we're not just building little islands of IP anymore. Most of the time, we want a fully converged network that brings together cloud assets and brings together, remote assets. And so we're not just building a little island of IP in a control room. We're connecting remote sites together. We're integrating compute resources that may exist on the cloud, in public cloud or in private cloud or elsewhere. And so when we're building these things, we need to make sure that we're thinking far enough ahead so that we can accommodate future growth as we're building our networks. When you're going through, these processes, one of the most important things I like to focus on is a lot of this is not just one person sitting down kind of making out a plan. You need to bring together the human element when you're building these networks, because you're not typically working by yourself. You're working with multiple organizations. So you need to start off with an extensive workflow discovery. You need to configure out your contribution sources, your destinations, how you're going to remotely access these things. And you have to make sure that you're communicating with the client or the customer on how do we accommodate the security requirements of the organization and still meet our workflow objectives, because sometimes those things can conflict with each other. One of the biggest, most important things, sometimes you get to design the network, sometimes you have to work with customer IT. So bringing together all of your different infrastructure, your firewalls, routers, and making sure that you have a plan that not only accommodates the needs of the production, but meets in with the security posture of the organization that you're working with. The more you communicate, the more you document, normally the easier time you'll have working with your client. You need to figure out what type of topologies you're going to introduce, what's most appropriate for the application of your system, and then what level of redundancy is appropriate. We have a lot of customers that don't want to make the additional investment in having a fully redundant -7 environment, but you need to think about, how am I going to maintain the system? How am I going to upgrade the system? And then once you kind of consider those things, you'll kind of understand that maybe having a fully redundant network is necessary. And it also allows for stage configuration management and further testing. You got to understand your bandwidth requirements. Make sure that you understand your bandwidth requirements for the real-time hose of data. You also need to make sure that you have the bandwidth for any type of file-based workflows that you may have coming down the pipe. Different types of networks have best effort networks. Most IP networks are best effort, but sometimes you want to introduce police bandwidth to make sure you don't have oversaturated links, and you can do that with software-defined features, so similar to like Cisco IPFM or Arista MCS, or you can just build a completely non-blocking network and let it ride. You kind of have to consider into consideration, when you're doing switch planning or when you're building architectures, we're not in the days of, every single device gets a different port. We're using channelized optics, so we're, taking a 100 gig interface and breaking out into 425s, or a 400 gig interface and breaking out into 100 gig interfaces. What that does, it adds a lot of complexity into your physical layer planning. Before we'd have one device, one port. Now we are having cascading layers where things are fanning out, and it's really important to over-invest in your layer one planning, because once you've built that foundation, it's very, very difficult to change it while the system's running. You have to also consider how your devices are going to register, how device registration and discovery is going to work. Most of that's handled through NMOS, but are you going to use a static RDS? Are you going to use SDDNS? And what are the implications of deploying those two different technologies? You're going to have to figure out what devices are going to talk to what, and probably build an ACL matrix so that you don't want to leave your network wide open. When you're in your planning phase, it's really good to determine what devices need to talk to what other devices, so that you can start with a focus on security from the inception of your network. Documentation becomes really important. Here's documents that we've had in the past where we have a whole bunch of VLANs and things like that. What we're finding is that the documentation that we have, that we started with, worked really, really well in a baseband world, but we are having kind of an additional dimension to how signals flow, and so you're going to have to change how your documentation works. Like I said before, you need to really plan for the future. Make sure you over-allocate your address ranges so you can accommodate future growth. Make sure you pre-configure media ports to make future growth easier to implement, and then figure out if you're doing manual multicast address assignment, and make sure you avoid multicast addresses used by other protocols. I've had clients before use address ranges that are used by routing protocols and brought down their whole network. So there's kind of just little things you have to remember when you're planning things out to make sure you have a successful deployment. Documentation is a huge thing. Back in baseband, it was relatively simple. Everything was flat and on different layers, and it was easy to draw in CAD. And now with IP, we have kind of additional layers. We have single devices or single interfaces that may be doing many, many, many things at one time. So how do we represent that? Right now, but in the past, we were just in the past, we were just doing simple line diagrams because it was one cable, one signal. But now we have physical connections. We have different asynchronous software workflows that we need to take care of. We have data flow patterns that are happening through different control APIs. And we have to think of logical connectivity and physical connectivity as two separate things, along with how we're authenticating these sources and any types of credentials that we need to store securely and manage through these processes. The different types of documentation you have workflow process maps, configuration diagrams, line diagrams, spreadsheets, and something I've been starting to introduce when we're building documentation sets is just from the beginning, starting to build a relational database to store all this information, so you don't have to have multiple copies of the same information. You can build a relational database that ties together your sources, your destinations, your devices, their feature licensing, even purchase order numbers, all of that stuff, and bring it together into your overall system design so you can have a more encompassing documentation set. Kind of system examples, building out a simple process map for how we pull in sports data from a sports venue. I like to build these little process maps so we can see we have a sports venue, we have a scoring data feed, how that data gets pulled in from the TV truck and goes through the cloud, and build these nice little diagrams, because at the end of the day, we can't keep all this information in our head, and we have to share it and learn how to communicate this information to other people. Similar, we have line diagrams, which have been around forever. We have spreadsheets for configuring our switch ports, and we can also define device-specific information where we have individual devices and then all of the different multicast addresses that they may consume, whether it's for video, audio, comms, etc. One of the big things that I've learned is you make sure that you always focus on your PTP distribution and make sure that it's as robust as you can afford to make it. There's typically one thing that's always a thing that's discovered late stage in projects is often you may think you're the only, in an organization, the production team may be the only people thinking they're using PTP, but as I found, once you get things plugged in, that you'll have other parts of a sports venue or other parts of a system that are implementing PTP as well. So you may need to consider not only distributing PTP within your production environment, but providing it for other parts of the facility. I've seen lighting control systems that require PTP, HVAC systems that require PTP, elevator control systems. And so if those are all riding on the same network and you're distributing it, make sure that you discover that information and include it as part of your design process. There's a lot of need for audio devices, and make sure that you plan for typically to have a more advantageous per port cost. You'll probably still be deploying 1 gig copper switching for audio and ancillary data. And then you need to make sure that there's some devices out there that still kind of have uncommon device proclivities. There's switchers that want in-band NMOS and out-of-band PTP, and there's also devices that will have their NMOS on a tagged interface on the media port instead of just being in-band, so kind of a sideband interface. You have to, and that kind of comes to an issue where not all devices communicate the requirements the same way, and then overinvest in extensive fiber planning, and then build yourself a test kit so that you can do high-speed 25 gig or 100 gig capture. So when you have to go investigate some of these issues, you have that stuff available. One of the things that I've always thought about when we're talking about devices is we don't always communicate what a device requires the same way. When you pick up a piece of food off, or a packaged food item off the shelf, in the US we have this nutrition facts label, in Europe we have a very similar thing. We don't have that today for our broadcast devices. Different devices support audio different ways. Some devices want 16 mono, some want 2 by 8 channel flows, some want 4 by 4 channel flows. Typically, when you're reading a white paper on or a data sheet on a product, that information might not relatively bubble up to the surface and be apparent when you're making the purchasing decision or when you're doing initial planning. There's also different devices that have different PTP requirements and different announce rates. Most of that's been standardized, but you can still come into some weird situations with some when you're bringing together proprietary technologies. How NMOS wants to be delivered, whether it's in-band, out-of-band, or like I said before, with certain cameras wanting a tagged interface, that kind of sideband interface. You know, one of the things we need to do is because CMDB can be a little limiting on occasion. With some of the workflow attributes of a production system. So I've been using a typical CMDB database and then kind of extending out with some a slightly larger schema to accommodate the needs of some production workflow elements.
Do you see some kind of need for a standardization around CMDB?
I think that what I think would be kind of the goal. Maybe something I would like to see from the standards committees is if we could have a standardized model for how we want to document some of these systems, and a standardized database model I think would be key to that.
You know, you're obviously living the same life I am.
Mm-hmm.
I'm wondering whether that, to your point of standardization, I was thinking the same thing, and I'm wondering whether you, me, Adam a bunch of people like that.
Yeah.
If our bosses would allow us to do a standardized set of documentation,
well, right,
that would be useful, so
and
that the end user would know how to read it.
Right, and that's
we run into the same similar.
We each run into the same similar issues, and the thing is, we can't keep all this in the head. We have to communicate it with other people. Your organization does a lot of the same things that my organization does, and I think that would be a good thing for organizations like ourselves to work together and figure out what.
Plus, for the end users.
To read, understand, and communicate.
Read one data set.
Exactly. And so, if our bosses allow on such a thing,
trade contact
absolutely.
One more question. Keeping the documentation up to date.
Mm-hmm.
Today you see a lot of people starting to use automation for that,
mm-hmm.
with discovery and automating the documentation in databases. Yep. Have you tried some of that?
I have done some automation of updating documentation, doing tie-ins with Cisco IPFM and things like that to pull information back out, tying in with orchestration systems such as Magnum or Magellan to pull dynamic data out and update basically views in that database. And that it works well. It's a little clunky. It takes some refinement and some effort to kind of develop the to pull the data you want and make sure it's the right data. But I think that's going to eventually be how we document these systems, is basically in real time by.
One of the reasons it has to be extensible is, to Adam's point about knowing the workflow in advance, many of the end users and organizations have no idea what their workflow will really look like at the beginning of the project. So if you don't build it out in an extensible fashion, you end up boxing yourself into a corner when you find out how they're really going to work. You've just got to make sure that you're dynamic enough to adapt to that. Yeah, and thus the database, unfortunately, I end up customizing a database for almost every project, and I hate that.
Exactly, and that's the struggle, right?
Yes.
The problem is that the documentation gets time consuming compared to the project time.
And it changes, so to his point about the relational database, you end up doing, if you can do single entry, where a change in this tab of a sheet changes everything else, then you keep it straight. If you've got to do it on drawing after drawing after drawing, and you've got to do it on spreadsheet after spreadsheet after spreadsheet, the question is only how many times you will go out of sync on a project, not whether.
Yeah.
You need to have it automated with IT, so that we need to have it automated. You need to have it automated so you can without manual work.
Exactly, and making that investment in automation is sometimes hard to rationalize in the beginning of a project, and then at the end of the project, it's like, oh, why didn't I spend more time figuring out the stuff ahead of time? But all of these projects are typically rushed endeavors. Normally you have less time than you want, and at the end of the day, you need to get the system working before you need to have it fully documented most of the time, and so it's always a struggle.
There should be no reason why broadcast controllers and stuff like that
Couldn't provide all that information.
provide all the information.
Yeah, and so working, with standards committees and us together, I think working together to kind of come up with a schema for how that, or APIs for how that data becomes available and brings together, I think would be an important effort for us to all work on. Well, thank you, everybody. I really appreciate your time today.
on the water. Thank you everybody for taking time out of the ride to take a little boat cruise with us. On behalf of Ames, AMWA, and BSF, we like to welcome you to the boat. And for those of you who do not know who I am Tina Lipscomb. I'm the operations manager for all three organizations, Ames, AMWA, and BSF. So you may have seen my name around, but basically if you need any information about any of those organizations, I'm the person you reach out to. So we have two speakers today. The key will be when we turn the boat around, that's when our second speaker comes up. So, and then we'll return here right on the top of the hour and get you back so you can go right back inside to the ride. If you need anything, more coffee or anything like that, please just motion, and our wonderful hosts, Nora and Faye, will help us out, and then we have our Captain Marta, and she will take us on our great cruise today. So thank you very much, and Gus, I'll hand it over to you.
Right. Thank you, Tina. Good round of applause for Tina. Putting up all the efforts, and all the ladies and the captain and everything else. Well, are we on, Brad?
Yes.
Well, thank you, first of all, for being here, taking this time. My name is Gus. I am currently working for Netgear, celebrating my 2nd year anniversary today, actually. 2 IBCs ago, I started, and I'm proud to have survived. Well, today we are going to talk about how to think your network from the protocol or from your AV over IP transport of choice, right? So, has everybody ever tried anything with a protocol called Dante? Yeah, very much familiar? Anything with something in the video aspect like NDI? Yeah? So these are proprietary protocols. That's maybe something that not everybody understands, but in short, anything that is proprietary has one company supporting that. And open standards or protocols or technical recommendations are then based on the alliances that Tina was starting. I will focus on the open standards today. I think that IPMX and ST2110 are in kind of the buzz for this show particularly. So every time, and this is my agenda, but at the same time is like your checklist for your next project that you will start. I suggest you always start deciding the application or listening to your customer, but once that the use case part is sorted, you will have to choose an AV over IP protocol just to stay within a certain ecosystem, right? So if you are seeking interoperability, there are interoperability options also with the proprietary protocols. But today we're just going to focus on open standards. If your protocol requires timing, synchronization to the very detailed level, this is a must. You need to take that into consideration at the very beginning of your process. I am talking about PTP, but we're just going to talk about synchronization in terms of many interactions that must be live and instant, and you cannot face or tolerate any delay. Some other applications like a single source to single destination, maybe you don't need much of that. Then you will have to calculate your bandwidth. So bandwidth sounds like something that goes like this, as in a width. I prefer to talk in speed. So if we think of how fast our lanes must be to transport everything, I think we do ourselves a better job in naming things right. So let's talk about speeds as well today. Finally, you will want to start your project today and make it survive for the next, hopefully, and I would say at least 3 years. Guys, 3 years is nothing. But in 3 years, I expect our industry and let's say the world to change a little bit. So we need to prepare for scalability, also for things that we not yet use or we are not even considering. So always start your project thinking of the day, the moment, also the bill that you will charge your customer for scaling that. Finally, techniques as in optimizing your cabling infrastructure with PoE. Everybody familiar with PoE here? Yeah? Great. And also redundancy. I want to pick your brain here. Who has ever worked in an IP media system that needed redundancy? If you want to share your experience, just pick the microphone, please, sir, if you can share. Can you share?
No, I mean, it's just all of them.
All of them.
Yeah. No, it's
Just for the recording, please. Yeah.
sure, no problem. So, I mean, when you're doing, high-profile events, contribution quality video, everything has to be fully redundant. If you're not doing that, then you're just begging for trouble. I mean, there's always going to be something failing.
Definitely. I just want to comment on that because redundancy is measured in levels, right? Theoretically, there is no full redundancy. Otherwise, you will have to have two talents, like the cover band right there, the tribute band, two cameras for everything, two or more. So we have some strategies to improve your redundancy within the network. Finally, the topology design and optimization. So has anyone here ever seen a network topology where you literally see the switches connected to the routers, connected to the APs, and then all the physical connectivity? Well, that should give us a little map, but as we know, in the IP realm, everything works in logic. So sometimes we will see something that is connected, but not necessarily everything is going from point A to point B exclusively, right? Just leveling up a little bit of our understanding for the conversation here. Well, I'm proud to be, as I said, celebrating my second anniversary in this company, which has been the one switch manufacturer that has heard the industry and has understood that you not always will have the chance to just work with one protocol. And as we said before, scalability means being ready to rock with the next improvement, with the next development that the industry might show us. So Netgear AV is currently supporting over 480 partners, which are, I think, 200 just in this show. And if you go to ISC next year, you'll probably see the other 300 there. We are, let's say, working as much as we can to simplify networking deployments for AV professionals. Basically, we want you to see our Netgear switch and just trust it. Say, okay, I know the ports that I need. They are configured the way I need. All of this configuration, we made it easy with a profile. So what we, as Netgear, call profile entails is a big list of configuration that are optimized for your Dante, for your NDI, for IPMX, for ST2110, and even hybrid networks, which is the topic for today as well. So I want to start just saying that in our case here, if you think of the average AV mindset, we want to control, we want to see the lights flashing, we want to monitor everything, we want to be in full control of our network and endpoints. So Netgear offers a software that is free for download, and you don't even need to install it anywhere. You can just walk around with it on a USB stick, stick it on a computer that is, of course, connected to the network, both wirelessly or wired, and the software will discover automatically all the Netgear switches that are in place, allowing you to have instant visibility of your topology. The software is very complete. I just want to pitch some of the trainings that we do at the Netgear Academy that is dedicated to the software, the Netgear AV Level 2 certification, where you can have a little, like a tour on the software and on its capabilities. Once again, it's free. You can download and stick it on a USB. Hopefully we'll have some cloud implementation in the future. Well, with Engage, you will be able to visualize. I know that it's probably hard for you guys to see over there, but trust me, what I'm showing on the screen here is our topology view, where the switches are displayed like a little thumbnail that reflects the unit, and you can see the uplinks. And by double-clicking any of these uplinks, you can see the traffic. Why does that matter? For example, please, just use the microphone, please, my friend.
How does it work? Through SNMP or HTTPS in order to discover the devices?
So we use MDNS to discover our own devices, and then with a little handshake, they start exchanging information. So SNMP is also capable. Our switches and Engage itself could serve as an agent for SNMP servers. But as a company, I would say we are acknowledging the historical contributions of SNMP, but we're certainly looking for more API-based and libraries that end users, integrators, or other manufacturers could also have in their hands. Good? Please, one more question. Microphone, please.
How do you provide network security and integrity? How do you make sure that somebody that's getting on with your software is authorized to be talking to the devices that they're connecting to, especially in the automatic realm?
Sure. Well, all of the devices that are discovered, they are discovered after you create an account with the software, so you're locked behind your password. And here on the top is very small, but the same software could be controlling several networks. Once you have visibility to the network itself, you could even go as far as putting one password and a limited set of users for each site, as we call it. Just think of a site as a collection of devices in a certain venue. So this is definitely protected by passwords, and if someone will simply plug in a computer in one of those ports that should be available, they will not be able to see it. I mean, they can have Engage themselves, they can have their own accounts on Engage, but if Engage under another account has already onboarded these switches, they are locked in. Okay, good. So far I have the answers, please.
Can I just quickly clarify, does that include networks that are isolated from the internet?
It is isolated from the internet.
They can be isolated from the internet, you can still do all the logons and things. It's
Absolutely. You need no internet gateway to talk in the LAN, let's just say it like this. Well, after discovering all the devices, you will start configuring. I will try to be fast in the next 20 minutes, just showing you what devices we would see mostly being recommended for IPMX and then for ST2110 at the end. Well, our, let's say, flagship and best sellers are the entry level, which are the M4250. Just take a little mental note of this 4250. The numbers will grow as the capabilities will grow, but this is the bottom level where most of the switches are 1 gig on the access ports, 10 gig, either copper or fiber on the uplinks, PoE to a certain level, because we understand also that PoE is what makes a switch mostly expensive. And on the M4250 line, you will not have redundant power suppliers. So we can call it an entry-level switch. Very affordable. There are units that start from 500 euros with PoE, with all the AV profiles that I mentioned. So with a simple, let's just call it not simplistic, but simple as in humble, M4250, you can have it all. You can have your NDI, your Dante, your IPMX. You can have the so-called 1 gig world flying through these ports here with all the best of your capabilities. You can split the ports into different VLANs as one would. You can interconnect the devices and just build and keep on scaling. Engage will always recognize a new switch. If you have already some, let's say, site-wide rules and policies, the new switch that will come into that will just adhere and adopt those in terms of DHCP, VLANs, ports, etc., etc. Some of the faster, as I was saying, more bandwidth but faster devices we have will also have fiber ports that can be lagged, that can be aggregated together. And this process of lagging two switches, or please.
No, I was waving at the child.
Ah, the children. Are you learning something? Okay, good. Well, the process of grouping ports together to increase the speed is called lagging. And on our portfolio, we have very good features that automatically do this for us. This here is our, let's say, core device within the M4250. When I say core, it's not that it's my favorite, it's just that it could be placed at the core of your network, and because it has only fiber ports, it is certainly not expecting end devices, endpoints. So this one at your core, 16 times 10 gig, connected to one of the most simple ones, you are in 1, 2, 3 switches ready to have and deploy a robust, I would say, robust and solid network. Well, After you have,
When you have 16 10 gig ports, does that mean you have 320 gigabit backplane on there? Or?
yes, sir.
Okay, so it's full line rate, no restrictions. Okay.
Correct. Are you familiar with what the question was about? Non-blocking architecture. So basically what he said is if one elephant can come through each of these ports, all the elephants can coexist in the room inside. And yeah, you're fast on the math, so kudos. Well, once you have, of course, the physical part set and done, you will want to logically break that into virtual local area networks that I just have a little representation here of how that would be. In our Engage software, this refers to the profiles. Once you have many devices that are interconnected, every port that will be carrying data from multiple VLANs will be automatically configured as a trunk port, allowing multiple traffic from multiple VLANs. Okay, so I know it's a little bit hard for you to see, but just try to concentrate on this topology. We're going to be building on it. So as I said, we have our fiber port 16X. The models at this point don't matter much, but just like think of a fiber port core, very fast with 320 gigabits backbone. And then you start putting your, in this case here would be almost like an aggregation layer and some edge access layers here on the bottom. All of this can be broken into as many VLANs as you wish, and because we offer the simplified AV profiles, you could just add the protocols that you wish. Of course, each of them will be initially contained into their own VLAN, which sometimes is what you want, and you can simply accomplish that in a few clicks with our Engage software. Well, as I said, once the ports detect multiple traffic from multiple VLANs, they automatically configure themselves as trunk. Now, we're going to get to something that Netgear does very well, which is the control of something we use a lot in AV over IP, which is multicast. So, primarily, initially, originally, let's say before multicast was carrying so much data as we have in AV, multicast was not that much of an issue with a few kbps. So multicast traffic should always come from the access back to the core, check the list of subscribers with the IGMP querier or boss of that whole multicasting, and then back. So this becomes a little bit problematic if you're working with video. If all the video that you want to split to multiple receivers needs to traffic all the way in the network just to know where to go, becomes a little bit complicated, and it will saturate your uplinks, will oversubscribe. The symptoms when this happens are certainly visible. You're going to lose frames, you're going to see glitches, you're going to probably see that the whole thing is not working. You're going to blame the network, but just remember, with companies that are looking for these challenges, as we have solutions that are one click away. But how the solution works is, I'm sorry for this maybe not too clear picture here, I'll try to explain it verbally. As I said, in these two switches, we can have multiple protocols, multiple VLANs. But let's say that we have a VLAN here, another VLAN here that are the same VLAN ID, and another VLAN here that all the receivers are contained into the same local switch. They are connected physically to this local switch. Our IGMP Plus would, instead of obliging all the multicast to go up to the querier and then come back, we can say, well, if all your subscribers are here, you don't need to go back to the IGMP querier. We call it a layer 2 multicast control method. Behind the scenes, what we are doing is that we're blocking all multicast on all uplinks, and we are sharing the vital information with the transmitters where they need to go, and then the switch, if there is a receiver on the other side that is subscribed to that multicast, just that flow will then be traveling across all the uplinks to the receiver. In a micro star topology like this one, it's easy to see the advantage. But as you scale, this becomes intricate. And we as AV over IP engineers, we just want to have freedom to keep on building on our networks. Without IGMP, the scenario would be a full multicast flood. Again, loss of data will be just dropped. Again, the slide is a little bit wiped out for the light here, but without IGMP Plus, all multicast, regardless of where the receiver is, must go back to the core in this sense and check with the IGMP querier what would it be doing. If you still need more bandwidth, we're still talking about the M4250 products here. If you need more bandwidth, you can group ports together, particularly on the uplinks, and allow 2 ports to work as a single logical link. This scenario is very common. However, if you simply do this without worrying too much, you may create a loop in your system. So particularly broadcast messages without lagging could come here, get here, and be looping in, again, bogging down, slowing down your network. That's why in our switches, we have a feature called auto lag that will simply understand that, particularly with broadcast messages, and will say, well, these 2 ports are now working as one. Let's just allow this to happen. To conclude this network, as I see we're turning back now,
Yeah,
right?
Right.
I want to showcase the M4350 line, and I'm just going to show a nicer topology here where we could have this kind of clearly visually represented. No need to talk much about configuration at this point. Here, one back. Well, IPMX is tailored to be very flexible. It could potentially and theoretically can work with any size, right? We can work with any quality, any uncompressed or compressed. It could be working also with higher bandwidth traffic, but let's say it's oriented to the 1 gig market. ST2110, on the other hand, is definitely not on the compressed market. It must work with uncompressed video. It must work with live, real-time interaction of multiple teams on that. So in a scenario where you would have part of your network that is IPMX and part of your network that must be ST2110, you can still use that Engage software. You can still control all of, let's say, the variables of your network from the single pane of glass, having part of your network with the simple 4250s, the other part of your network with the more advanced, therefore also a little bit more expensive, 4350. So, just in a nutshell to conclude, our recommendations would be for IPMX networks and IPMX devices in general, make sure that you first decide the timing aspects, as we have discussed it earlier, if IPMX will be PTP based or not for single source, single display applications. For ST2110 devices, make sure that you configure the VLAN where all these ST2110 devices will be residing. That must then comply with the BC boundary clock control, GMs, and all the controls that we also offer in terms of NMOS and etc. The full stack of ST2110 is supported by our M4350. Double check that all devices are correctly configured to work as you want. Finally, use the M4350 ability to handle both. Of course, like the better can handle the least required, the least picky protocol. So if you create a system where on your core you have an M4350, M4250 for the IPMX, M4350 for your hybrid networks, you will be able to just like fly on the best highways for the AV over IP. Finally, I just want to summarize that M4250 for cost-effective deployments, M4350 when you want and need the full ST2110 support, auto lag, auto trunk, IGMP plus, let's say the best features of Netgear are automatically there. You don't need to do anything. And then at the end, just make sure that you perform the firmware updates as we get along. Hopefully you found a little bit of information in this session. Please, one question.
Real quick, Do the 4250 and 4350 have PTP boundary clocks inside?
The 4350 is a big product line from which 8 products do.
Okay.
They can be Grandmasters, each of them, and by that they can also work as boundary clocks.
Do switches which have GMC functionality also support GNSS input for synchronization of different locations? So for global navigation satellite systems input for time synchronizations between different locations. Do you have this support or no?
I think what you're ultimately going to have to do is have a GPS to PTP converter, let's just say, like a dual clock boundary idea there, to then ingest the PTP on the network, and then it's fine. One thing is for the endpoint AV devices to follow the network. Another thing is for the switches to synchronize themselves. So exactly what the GNSS that you mentioned,
For example, on some Cisco Nexus switches for 2110, they already have GNSS antenna input, and you can directly synchronize it.
Multiple locations.
Yeah. So that's what I thought, if you have it, maybe.
I think within our product line, we don't have this built in. You will need an external box for that.
Maybe just one more question
Please.
about the profiles you mentioned for the devices. If you have device which uses more different protocols, do you have some like trunk profiles for different protocols, or how do you deal with this?
Well, I think that if the different protocols are coming from the same Ethernet port, at some point you will have the IP problem, let's say. What are you talking, who are you talking to from that device? Maybe these devices will have multiple Ethernet ports, and then you just can connect them to each. Or if you're talking about a dual stream, something like a device that could send you uncompressed video and also a compressed video, I think those can operate on the same VLAN. You wouldn't need a different VLAN for that. But just to conclude, we also offer pre-sales consultation for free. So just reach out and I'm sure we can help you with your projects. Thank you.
Thank you, guys.
Thank you.
If I could grab your
Please.
tab there.
Yes.
Our next speaker, Nicholas. We've had it, which is our 3rd year. So he's a veteran at this. And we'll go right up until we get to the dock so that he can gather back a few minutes of his time, all right?
Yeah, I'm Nicholas Stroman. Some of you know me already. If you don't know me, just come speak to me. I work with Direct Out right now. I'm on the show in the behalf of Direct Out, but I have my own private company. I also do consulting network design. I have a big project with Netgears that we can talk about later if you want. But now we will talk about PKI and TRS on IPMX and NMOS, because, well, it will be a hot topic for the years to come, especially in EU, especially because of something called CRA. So yeah, more acronyms, of course. Wire secure communication, encryption, what is a PKI? What is TRS, NMOS, and IPMX? What do they use? The caveats and future proofing. And, well, how do we do that at Direct Out? Because why not? So yeah, just for the history, it will be in the presentation on the website. PKI, Public Infrastructure, TRS, Transport Layer Security, CA, Certificate Authority, OCSP, Online Certificate Status Protocol, CRL, Certificate Revocation List, IS-10, well, that's NMOS, we know that already. BCP 003, that's an NMOS best common practice about securing NMOS. And this is the most interesting in the context of this presentation. So why do we want to do that? We want to avoid spoofing, device impersonation. We want to avoid attacks by API tampering, and we want to avoid rogue flow interception. And of course, we have the compliance driver. The Cyber Resiliency Act, this is for all of the EUs, not only the market of broadcast, but of course, we have the lovely EBUs with another recommendation. And this one is already in tenders. I was working with Direct Out. I am helping the company answer some tenders, and of 143 is already in the tenders. Do every manufacturer respect 143 at the moment? Definitely not. Okay, so it's a business requirement. I did that. I said that already. But CRA is, of course, more than just certificates. We will just take the certificates today and let's move. And yes, cybersecurity is about authentication, encryption, and the both combined. So it's not just encryption. Because you have a flow encrypted on the network doesn't mean it's secure. It's about the authentication. Is the source of my flow the source I can trust? So the problem with I get that every year. It's very slow, but it will eventually. So the problem comes from the types of encryption. We have two types of encryption. Symmetric encryption, which is using the same key. This is what you use when you are sending an encoded zip file. You choose the password of the zip file. The zip program is actually generating a key from this password, and you tell the password to the person that is required to open the zip file. This is very fast, but the keeper of the secret is you. You give the password. And if the password leaks, then it's wrong. But if someone takes the zip, has the password, it can forge a new zip with the same password, and you can open it and use the data in this zip, and you have no way of knowing that this zip is actually authenticated from the source that you expect it to be. This is why we are using asymmetric encryption. Asymmetric encryption is using a private key and a public key. The public key is a public known information. It's not a secret, so you can share it with anyone. But the private key, this is the ultimate secret. You keep it for yourself. And by signing with your private key, the signature can be authenticated with the public key. Sounds familiar with some of you? Because you use that actually every day. Every time you are on a HTTPS website, it uses an X509 certificate. And a certificate is signed with a private key, and it supports, so yeah. It is signed, and in the certificate you have a list of features on the certificate. For instance, I have this key, it has a certificate. What can I do with this key? I can sign websites, okay. I can sign email, okay. I can generate new certificate with the certificate. That makes this certificate a certificate authority. Or I cannot. And slowly, we are transitioning into the public key infrastructure. Yes. So who does issue the certificate? Maybe right now you are using HTTPS on your broadcast devices and you have self-signed certificate. So you sign the certificate yourself. Once again, who authenticates that you are signing yourself? Who authenticates the signature? Because it is self-signed, there is no way to authenticate that you are on the origin of the certificate. It's a matter of trust and of third party. You always rely on a third party to ensure that you can trust the communication between two parties. The third party will not necessarily distribute the keys for the encryption, but the third party will make sure that the sender and the receiver of the encryption are the right people. So if I put a web server ibc2025.director.eu with a secured HTTP connection, I will have an information on my browser saying, I cannot validate this certificate. Why? Because I cannot put it in a PKI, a public key infrastructure. And actually, the system is asking you to decide. So because the certificate is not automatically authenticated, the system is asking you to decide. In a PKI, you have signature, and the signature is authenticated. So like what we used to do with checks when we were using them. And to do the authentication, we will use a PKI, but also we can revoke the authentication with the certificate revoke list. So if in the certificate there is a line that says you can find the list of revocation from this certificate. If the certificate is a certificate authority, this means that you can generate certificates and you can also remove certification of the authorization list. So it's like distributing a key to someone, and then you can keep the key, but I change the lock. Like I did with my ex-wife. I'm kidding. So yeah, finally, the public infrastructure. So this is a chain of trust. The public infrastructure consists of a root certificate. The root certificate, you have to authorize it. You trust it. You do an explicit trust of this certificate. You actually do that every time you install Windows or Linux or any system and the browser, because there are 4 or 5 institutions worldwide that are secured and generating most of the certificates that are used on the World Wide Web. So their certificate is embedded in all the systems, and they will generate a chain of certificate until we get to the chain ibc2025.director.eu. So the generator certificate, the owner actually will generate a private key, a public key. The certificate will be signed by the root certificate, and then the owner of this certificate, if it's a certificate authority, will be able to generate a new certificate that is signed, and at the endpoint, the browser will go up the chain, validating that, okay, this is by this certificate. I don't know this certificate, but this certificate is signed by this certificate. I know this certificate. So going down the chain, I can make sure that I trust who gives me the certificate. And once again, why do I trust? Because this certificate is encoded with the private key. Actually, because I trust this certificate, now I can use the private key of the certificate, meaning that the server can encode secrets with its private key, and I can use the public key to decode it, and it will be authenticated from this. Double click. Yeah. Okay, so the best practice around that, and this is, I mean, 4 months ago I was not an expert, and I don't claim to be an expert right now in certificate and security, but I had to learn that. So it's basically what motivated this talk, to help you speed up the learning curve. And the best practice is, of course, the private key must not be shared. So right now on some devices, you even have the ability to generate CSR, certificate signing requests, mean that even the private key will not get leaked. The private key will stay inside the device. If you know the old way is that you get on your PC, you generate a certificate, and then you copy the private key into the device, and you copy the public key into the device. This is bad because you copy the private key, so the private key leaks. You can tell me, and I trust you, I did it with the best process, and I am sure that the key is not leaked. Yet, but still, there's a human in the chain, and we love human, but they can't be trusted. Again, my ex-wife. So they are really needed. They are really needed. On the other way, when who is the free signing authority for website? I lost that. Let's Encrypt. When Let's Encrypt is giving me a certificate, well, it's kind of loose, and it's giving me. So it's not really a big. I'm not really a big my element in the chain of trust, so the trust and the security here is quite close. Yeah, so it's a secret. So this is important to know. When it's a secret, the more automation you involve into generating the secret, and this is BCP 003, the more automation you involve in the secret, and the best is the secret. So how do we use TLS? TLS, which is actually the technology that the HTTPS is using, it authenticates the endpoint, so the server, secures the communication, use an asymmetric key to exchange actually a symmetric key that will be used for the communication. But because the symmetric key is generated between a secure communication between the sender and the receiver, the exchange symmetric key is known only from the server and the receiver. It ensures confidentiality, authenticity. And let's say NMOS and IPMX. So NMOS IS10, it handles authorization. Who am I? What rights do I have? BCP 03, it's TLS, HTTPS, and you can go, BCP 02 is automatic provides provisioning, so it ensures that the secret is not leaked, etc. So IPMX uses NMOS, but when a stream encryption is required, it will use PEP. It's in the phase of standardization, let's say like that. And I have 2 more slides, and you will be free. Yeah, so the media streams, right now there's PEP that we are talking about, and the issue with the private key is also the problem of the secret. If there's a symmetric key to encode a private stream, how do I make sure that the secret is safe? And with ST2110, there's a lot of multicast, so there's an issue with that. If we have a group of receivers and they share the same key, and the group change, then the receiver getting out of the group should not have the key to decode the flow. But it depends on how the level of, what is the level of security do you want to do. So PEP I will let for later. You can look at the presentation online, but basically it has everything it is needed. But there are also, of course, caveats. So authentication encryption does not compensate for network segmentation. And if you are doing broadcasting, you are most likely segmenting your network, hyper-segmenting your network way more than VLANs. Proper use of rights management. I was installing a system in a school last week, and it told me, yeah, just make one account for every one of us. No, I will not. You can use one account, but I will not make one account because I will not encourage you to have weak security. Ciphers are not perfect, and there will be a slide after the discussion that you can get online with the time that is needed and the list of different ciphers and their status right now. Yes, always needs maintenance and vigilance. And if you are a product designer, you know that there's lots of EU recommendation and enforcement coming up that will require you to disclose the vulnerabilities. So at Direct Out, we provide our own PKI so that it's plug and play. You will install the PKI, and then every HTTPS server will be recognized and authenticated. It's not released yet. This is done in the short term, and in the midterm, we will also encrypt flows. But midterm because it has to go fast, but not short term because it's not decided yet. Okay? And there we are. Any questions can be...
We have time.
We have time?
Yes, you have time.
Perfect, perfect. Yeah, so I will have this slide just showing and then ask you for questions. Yeah.
So what you mentioned for the encryption of 2110 streams, which you have in midterm roadmap, this is only on the output side, right? But how it is on the source side? So do computers or I don't know, microphones, audio mixers have like way to upload private keys or certificates on them directly, or how does it look in practice?
This is a complicated part, and you can understand that from a standardization point of view, it's very complex to standardize something that is inherent to the workflow and to the solutions that are provided by different. And eventually it comes down to the broadcast orchestration. So if you have a broadcast orchestrator, I bet you that it will be in charge of distributing the keys, of making sure that there is a good distribution of keys, a good secret, renewal, etc. Of course, if you stream, even if you stream to the same target for a long time, you want the key to change, just because the longer you use the key, the more data you give someone to use to guess the encryption key, so you want to change often. This is called key rotation. So the issue there is that there's a third party. It will probably be the broadcast orchestration system. And how will it put the keys on the sender? How will it put the keys on the receiver? And how will it connect? And I guess NMOS will have a solution for that, but it's only a guess. No more questions?
I have. What do you see? What are the biggest threats in media for security? Is that data leakage, as in people trying to hear in the conversation, and then variously.
Yeah, that's what broadcast people would tell you. But working on system, the biggest threat is the users. The biggest threats are your colleagues. And not because they are dumb, because they are far from dumb. It's because under pressure you make mistakes. And the simplest example, just to bump on your presentation, is the lights. So on some switch, you have the lights for the VLANs. Okay, so you plug on the right VLAN. You really think that when you are on the backstage under a lot of pressure, you check for the light, or you remember the good color of the light. So, yes, there are processes, but when a user is involved, this is where error happens. Try DHCP versus static IP. Who here has entered more than 50 static IPs and not make one mistake? Okay? So, at the CBC, I have a friend at the CBC, he had an Excel with 3,000 lines of IP.
Quite small for a 2110 system.
It is, but the issue there is that, of course, you have a lot of verification to do, and it's costly. So the more automation you get, the better it is. So yes, the users are the first. Then, of course, some countries that are against our way of life, let's put it that way without being political, might be interested in hacking. It has been done before. In France, for instance, we have TV5 that has been hacked a couple of years ago, and it was really dumb. It was a subsidizer, a consultant that had a VPN connection, and they just did social engineering on the consultant. They went into the system. But this is why right now we have gateways everywhere and bastions, etc. There was one last question? No? Cool. Then, if you want to continue offside.
Tina.
Come on, that's it. You'll have to sit up here in the front.
Sorry for being so close.
Oh, it's okay. All right, hello everyone. Great to see a full boat. I see a lot of familiar faces in the crowd. That's great. For those of you that don't know me, my name is Spencer Deem. I'm a marketing manager at NextEra Video. We are a technology provider. We help equipment manufacturers add NMOS and 2110 and IPMX to their own products. So today I'm going to start by talking about the evolution of NMOS for 2110 and IPMX. It'll be more of a high-level overview. My goal is to help you understand what NMOS actually is and how it works. So a quick overview of what I'll be talking about in the next 20 minutes is what exactly is NMOS. I'll give an overview of all of the different NMOS specifications. I'll talk about some legacy broadcast applications of how NMOS is used in a broadcast facility for production. I'm also going to talk about the evolution of NMOS. How are we using NMOS for Pro AV and IPMX? And then I'll go on and talk about security, how you can test NMOS, and how you can try it yourself. So, what is NMOS? NMOS is the Networked Media Open Specification. It was developed by AMWA, the Advanced Media Workflow Association. And this is an open specification. You can go to the AMWA website, you can see exactly how the specifications work and how to incorporate it into your own product. And what NMOS does is it enables the true interoperability between different vendors' products in a 2110 or IPMX environment. So this gives you the true plug-and-play functionality and push-button simplicity of any AV over IP routing. So as I said, there's many different NMOS specifications. It can look a little bit like alphabet soup. We have these IS specifications. We have BCPs, which stands for Best Common Practices. It's a lot of different numbers and names, but I'm going to try to help you understand what they all do and what they mean. So there's a new initiative within AMWA to try to make it easier to understand. And what AMWA has done is sort of split up the specifications between NMOS Connect and NMOS Control. So some of these specifications are more for the connection of these NMOS devices, things like, resource management, connection management, and then eventually we're moving into NMOS Control, which is things like actually controlling devices. So within NMOS Connect, which is what I will be mainly speaking about today, is resource management. We have the common ISO 4, which is the registration and discovery. And there's a couple of BCPs that have built upon that and added things like labeling. How can we organize our NMOS devices with labels and grouping and some tags and things. And then there's also some automated ways to make it easier for your NMOS devices to connect to the network. You may have heard of connection management, ISO 5. I have a couple slides on this coming up. And we've built upon that with audio channel mapping, where you can change your audio streams and embed them into an SDI stream or keep it into IP and have a map of inputs and outputs. And finally, there's a lot of different supported functionality and codecs, things like JPEG XS. We're adding features to be able to have JPEG XS, H.264, H.265, MPEG TS is a new one, and NDI as well. So why should we care about this whole NMOS thing? Well, in the early days of IP, you had to have a system integrator, you plug in all your devices to the network, but you had to sit there behind your computer and type in all the IP addresses, and it was very time-consuming, costly, and error-prone. You have to type in all these manual IP addresses for every device on the network. So we said, there must be an easier way, and that easier way is through NMOS, and that gives us the plug-and-play functionality. Plug-and-play is fun. It's much better than plug-and-pray, as we said before. Also, most new broadcast facilities are specifying NMOS, so they say, if you're making an IP product, a 2110 or an IPMX product, we want you to speak NMOS because there's a lot of great features that come with it. And most all control system providers have fully embraced NMOS. Almost all of the broadcast controllers, we'll say maybe 99%, are embracing NMOS fully. So we're trying to get that remaining 1% to jump on board and use NMOS as well. So in addition, there's this article from the EBU back in 2020, the early days of NMOS, and they saw the capabilities of NMOS and wanted to support it. So they had this article, minimum user requirements to build and manage an IP-based facility. And they say, you shall use NMOS ISO 4, you shall use NMOS ISO 5. We know this is something we want in our IP facilities, so if you're building products, you should implement these features. So as I mentioned earlier, there's kind of two separate groups of NMOS. So there's what we're calling NMOS Connect, and there's NMOS Control. For my presentation, I'll be mainly focusing on this NMOS Connect portion. And first, I'll start with some legacy broadcast applications. How are we using NMOS in broadcast facilities? And then I'll talk about Pro AV and the end of the feature. So how does this NMOS thing work? Here's a handy diagram that shows a little bit about ISO 4 and ISO 5. So in a broadcast facility, you have all these different devices. It could be cameras, it could be gateways, maybe you have a monitor as well. So you have all these NMOS-enabled devices that automatically register to this RDS, this registry. It's a registration and discovery service. They automatically register, and then this control panel, it could be just a simple, push-button control panel to switch sources. That gets a list of all your devices from the RDS. So it queries the RDS, and it gets a list of all the devices that are connected to your IP network. And then when the user wants to switch sources and they press a button on the control panel, what that actually does is it queries the registry and it commands the receiver to join a new stream. It uses this IGMP join to join a new stream to switch sources, and then it commands the receiver to leave the previous source. And then that does the seamless switching. That's the source destination take that everyone's used to. So I talked a little bit about ISO 4 in the previous diagram, but what exactly is ISO 4? Well, ISO 4 does the registration and discovery portion, and in simple terms, you have all these devices on your IP network, and you have your NMOS controller. In this case, it could be a Conduct IP or any other NMOS controller, and that just announces to the entire IP network, hey, I'm an NMOS controller. Is anyone out there? Are there any NMOS devices on the network? And then automatically, any NMOS devices on the network will respond and say, yes, I'm a gateway or I'm a camera, let me register. So it automatically registers to this RDS using MDNS or DNS-SD. So ISO 5 is kind of the part that goes hand in hand with ISO 4. This provides the connection management part. This is what gives us the seamless switching. So ISO 5 enables that switching through what we call activations. And the activations can be either immediate, relative, or it can be absolute. So you could say, I want to do that switch now. You press the button your source destination take. I want to make that switch now. Or you can have it make the switch in 5 seconds, or you can have it make the switch at a set time. So if you want to look into some of the NMOS parameters, it's just a set of APIs. It's all in JSON, which is easy to read. And the way you access that is you just go onto a normal web browser like Chrome or Safari or something. You navigate to the IP address of your NMOS node and then /x-nmos. And there's a couple of different API endpoints where you can see the parameters of your sender, receiver, different devices on the network. So as you know, there's a lot of parameters involved in configuring an IP facility, things like different API versions. You have PTP, domain and announce intervals, different system IDs, lots of different protocols. Wouldn't it be nice if there was an easier way to automate these? Because we want that plug and play functionality. We want to just plug something in and have it work quickly and easily. And that's exactly what ISO 9 does. So this is an NMOS specification for system parameters. And what ISO 9 does is it provides an automated configuration of the media nodes. So if you have an NMOS device, you plug it in, and then all the devices on the network know all of the startup parameters in that facility. The way ISO 9 actually works is it's a server. It could be a little like Intel NUC here. It's a little DNS SD server. It has all of the parameters already programmed in there. And then when you plug in any NMOS nodes or devices, they read all the configuration info on startup and automatically have all of the correct configuration information. So when you have so many NMOS devices, you could have things like a camera, a gateway or something, and within a 2110 environment, remember every flow is sent as a separate stream. So you have your video flow, your audio flow, and your auxiliary flow. But we want to make sure that these, if you want to route them together, we want a way to tag them and say, okay, these all belong within the same flow. And we can use this best common practice for grouping. It's a way to say, okay, say I have a gateway here, and there's video, audio, and auxiliary flowing through it, but we want to make sure that all those flows are sent together. We can use this best common practice of grouping. It's actually called a group hint, and it's almost like a hashtag, and you say, okay, this is all together. I want these all to be combined with this playout master flow. So you're combining multiple video or audio or auxiliary flows all to one and making sure that they stay together. So NMOS has further built upon that idea. So the last one was called group hints. That's natural grouping of resources. We also have a way to have more tags and things. So this is especially relevant in these days where there's more software-defined processing. Maybe you have a multi-function box that's in a server room somewhere, and it can either be a format converter or a multiviewer or a keyer. We want to actually see what that NMOS node is doing. So there's a standardized way within NMOS to say exactly what is this device doing. It says you should say what the manufacturer is, what the product name is, an instance identifier, which is an easy way to see, okay, where is that physical product located? If it's in a server room, maybe you'll say, all right, that one is on floor 2, rack 1, position 5. This is the device that we're talking about. And then in my example of the software-defined processing, which is more and more relevant these days, that device could run any number of apps. So it's important to see what is the current function of that device. And in this example, it could be a format converter, or it could be a multiviewer or something like that. So there's also another specification for audio mapping. Again, because in 2110, the audio, video, and ancillary is all sent as separate streams, we can actually use that to our advantage. And if we want to combine multiple audio output channels and embed them into an SDI stream in a gateway or something, we can actually make a map of different audio input channels and map them to a specific audio output channel. And what that looks like is, here in this example, we have maybe 2 different audio streams that have 8 channels each. So stream 1 is channels 0 through 7, stream 2 is channels 0 through 7. And then we have our 16-channel audio output. You can have a simple matrix like this and just choose which input audio channels, that you want to route to your audio output channels. And you can have any combination of input channels mapped specifically to your combined audio output channel, either in SDI or IP. NMOS also supports what we call event and tally. This is ISO 7. And this is a way that we can send GPIO over IP signals using NMOS. This leverages ISO 5 for the connection management. And this is just an easier way to send something like a tally signal or a tally light, or maybe you want some dynamic text. And the way this works is you have a sender, maybe in this case it's a production switcher, and you want to light up a tally light on a camera. We can use ISO 5, and either using WebSocket or MQTT, there's a way to actually send that message to the receiver and say, okay, please light up that tally light or display this dynamic UMD. So that's sort of what NMOS is currently used for in legacy broadcast applications, but we're also using NMOS for Pro AV, and now that IPMX is gaining a lot of traction, we've developed NMOS to support IPMX as well. So NMOS has evolved a lot for Pro AV. So how did we make NMOS work for Pro AV? Well, we have a couple of BCPs. It's called NMOS for JPEG XS, because again, Pro AV, they like compressed video, whereas broadcast is more uncompressed. So we have some specifications for, it's referenced by VSF TR10-8, which is NMOS for IPMX. It also refers to other VSF specs like TR08 for transport of JPEG XS in 2110. So this also leverages ISO 4 and ISO 5. It leverages the grouping that we talked about earlier. And what this does is it really just specifies any updates in a Pro AV environment to something called a session description protocol. This is an SDP file, and it uses this media type, this video/JXSV. So you know that your device is using JPEG XS, which is common in Pro AV and IPMX installations. So there's also a big new development. This is probably the biggest new thing for NMOS in the Pro AV and IPMX side of things. It's IS11 for stream compatibility management. And what this is essentially it's EDID over IP. So if you're familiar with how HDMI works and you have your laptop or something and you plug it into a monitor, that monitor actually tells your laptop, hey, I can do HD or I can only do 4K, so it tells your laptop exactly what resolution it supports. And this is what IS11 does. It does the same EDID over IP, so with that receiver. So I gave a little example in the HDMI world, but it also applies to IP. If you have, say, an IPMX device like a gateway or something, and the monitor only supports HD, it'll tell that device, okay, please only send me HD. So I have an example here, a more visual example of how this NMOS IS11 works. This is a very simple IPMX Pro AV application here. You have a PC, maybe a gateway, so it's HDMI to IP, over the IP network to another gateway, and over to a monitor. So everything is connected through the NMOS controller, and we want to leverage this EDID. So what happens is the monitor tells the gateway, okay, here's the EDID, here's my capabilities, and that flows all the way through the network and back to the PC. And there's different constraints, different monitors, different gateways, things can have different constraints. So in this example, maybe your sender can only send 1080p, 4K, and it can do JPEG XS and HDCP. Well, what can your receiver do? The receiver maybe can't do 1080, but it could do 720. But oh, it also does 4K. And oh, it also does JPEG XS and HDCP. So what this IS11 does is it finds that sort of the least common denominator, that commonality between the senders and receivers to make sure that they're speaking the same language. So what it actually does is it patches the EDID and says, okay, here's my active constraints, here's the commonalities between the sender and the receiver. Please make it 4K, please have JPEG XS and HDCP to make sure that everything is cohesive. And this actually tells the broadcast controller to send a new EDID to the PC to make sure that it's sending the correct signal. So what about security? This all sounds great, but we want to make sure it's secure. Well, there's a lot of different specifications in place. We use TLS and HTTPS, common IP security things. We also have authorization through some best common practices. We use certificates using TLS. And there's also an IS spec called IS10 for authorization. And this just makes sure that users are authorized to change an NMOS system. It uses JSON web tokens and OAuth 2.0, but what this really means is it just makes sure that users are authorized to change the system and maybe has a login screen, something like that. An example of how the security actually works is you have your broadcast controller, an IP source, and a destination. We use an authorization server and then send the authorization request to the server. It responds with a JSON web token, and then the controller will then send that activation with the web token to the source. The source will have to verify the web token is valid using a public key provided by the authorization server. And then that source will start transmitting its essence flow. Meanwhile, the broadcast controller also sends the activation to the destination with its JSON web token. That verifies with the public key also, make sure it matches. And then if everything looks okay, then it says, okay, you're authorized to receive that stream. So what if you want to test NMOS? Say you're a system integrator or you're an equipment manufacturer and you want to make sure that NMOS is working properly according to the specifications defined by AMWA and supported by the industry. Well, we made it easy. There's a GitHub right here. You can go to GitHub, to the AMWA page, and look up all these automated tests to make sure that an NMOS device is functioning as specified. And then what if you want to try NMOS? Say you set up a little demo or you're in a broadcast facility and you want to actually try NMOS for yourself. There's a free way to do that, and that's through the Riedel NMOS Explorer. You can go to the Riedel website, download this software, and this is a free and easy way to see all of your NMOS-enabled IP devices on the network. You have your nodes, devices, senders, and receivers. And there's also products you can buy, broadcast controllers that do the same functionality, that have better user interfaces. We like this one. It's a Matrox Conduct IP. This is a full-featured broadcast controller, and it gives you kind of the more familiar cross-point switch you get here with your senders on the top. These are all your IP senders. These are all your IP receivers. And with the click of a button, you can actually do that switching using ISO 5 and ISO 8 and everything. And it's a familiar way to do that push button switching. So as now the boat's turning around, a couple conclusions. NMOS ISO 4 and 5 are stable, they're mature, and they're in almost all new 2110 products. The control systems have been greatly improved thanks to spec clarifications and lots of interop testing. There's many interop events and testing events through the JTNM and AMWA and the VSF to make sure that everything is fully, truly interoperable and working to specification. Some of the new features I talked about, things like ISO 8 and ISO 9 for system parameters, make it really easy to get your NMOS devices automatically registered to the network. And this far surpasses the level of control that we had back in the SDI days. The security is a very important addition. We want to make sure users are authorized to change anything in an IP facility. And finally, there is lots of work still being done and constantly being done to expand NMOS for IPMX and ProIV. Things like the IS-11 we talked about. And new exciting developments are on the NMOS control side, where we're actually trying to be able to fully control devices using NMOS through NMOS control. All right, thank you. If you'd like to learn more about NMOS, or if you would like to see how Nextera Video can help you add 2110 or NMOS or IPMX to your own products, please see our live demo. We're in Hall 10 at booth C13. Thank you.
Surprise, surprise, I'm going to go talk about many of the same thing as Spencer did, but from a completely different angle. Who is Simplexity? The company I am from. We are a little small company in Zurich in Switzerland, and what we do is actually consulting and training 2110 and NMOS. And what we really care about is like, what do we really buy, what does it help, and what can we buy to help us in the real world. So this presentation is basically about, you know, what you could ask for as an end user and as a manufacturer, where you should set your priorities in implementing stuff. So we got a great overview from Spencer, what's there in NMOS, but so I'm going to narrow it all down and go through it step by step, based on an example where I just want to unpack an equipment and plug it in and see how much and what the steps are to make it operational. So, generally, what are the goals of NMOS? Again, slightly from a different angle. NMOS wants dynamic setups. Everyone wants it, but how real is it today, in broadcast particularly? But that's the goal, and we want to be independent of manufacturers. No driver for specific devices. That's the idea as well. And we want to use modern web-based technologies to leverage from the IT. Those are the main goals really NMOS has set. So why? Why should we want to do that? Ultimately, it's about cost reduction. And I believe the reduction of cost has a lot to do with operational costs you're going to have afterwards. If you want to train everyone to every detail, it's going to cost you a lot. In order to make it more automatic, it's going to save cost. So the infrastructure you're buying actually has to allow that flexibility. What you do with it, it's obviously your responsibility, but if the infrastructure is not flexible, you can't change your workflows. So I think everyone's talking 2110 and whatever, and yes, sure it's there, but I believe it's not there as it should be today. It's much too static. It doesn't really do what, you know, in many cases, what you initially expected from it. Now, plugging it in, getting audio and video flowing, moving it somewhere else and do it the same thing there. A lot of installations are even nailed down to interfaces, doing a specific signal. You can't just move over there and plug it in there and go on. It doesn't work, many cases. So, basically, it's a chicken and egg thing. If you accept what's there, and you don't go to the vendors and say, we want this to be different, they will not change because they think that's what you want. So this presentation is about a different angle on that one. So what are the steps to take a device into operation? I want to go through 5 steps basically. One is a setup step. Second one is the registration discovery. You recognize that from Spencer's presentation. Configure the streams, and no, they don't have to be static. They can be changing, they should be. And then connect the senders and receivers, and finally, monitor. Because whereas you had some XY matrices before, now you have a distributed system across your whole facility or even between facilities. This is not as static and behaving as you wanted it to be. You have to know what's going on. So the monitoring is very, very important. So these are some numbers. I don't go into the numbers here. I just don't care about them. But there is all the numbers, you can find these specifications. So let's go on a stage and identify the roles in this stage when I want to now start doing a play. I have a control software, I have some AV devices, and I have a number of servers in my infrastructure. So in the next slides, I basically want to show how this can be plug and play. So I'm going to basically use these 3 different players, the control software, the AV devices, and let's call it IT infrastructure of some servers, and see what they're actually doing when you start plugging in a device. So, learn the stage, the setup stage, right? The setup step of everything. What's happening there? The AV device, in my view, would go in there and ask for an IP address. You don't have to do that. That's why DHCP is there for. So it asks the DHCP server for configuration. And that has been invented something like 20 years ago. So the DHCP server answers with some of the information. It can do actually quite a lot more than just setting up IP addresses, but that's what we are going into now here. Then The next one is the AV device. As we heard, there is a specification for some global parameters of this setup, like a PTP domain. I don't want to set up my PTP domain. I want the system to learn it. So the next step is that guy asks the DNS server, the name server in the IT, hey, what's the address of my system API, like where I can ask all the stuff which is valid in my installation. And then finally, it basically goes to that place and says, hey, what's the PTP domain in this setup? I'm just simplifying here. It's asking more stuff, but that's what's counting for you guys. So there is a spec which you can actually, with using this, you can automate setting up the PTP stuff. Then as the next one, it asks for the control software as well as the AV device. They say, where is my registry? The same thing. You shouldn't have to type in an IP address of your registration server. It's there in the specs. You can just ask a name, a reserved name, and it asks for that name, and it will be resolved automatically. So that's the basic setup. Then the next one is basically discovery registration. The AV devices basically go to that registry, which they have now identified, and put in their senders, receivers, and a lot of more stuff, including their capabilities. And that ISO4 registry, the infrastructure, hosts that information. It stores it there. Same thing now, the control software says, who is there? I'm going to query and ask for all of this. So he knows who is there. And finally, it also says, hey, please send me updates if anything changes. So that guy wants to know what the current subscriptions and whatever is. So that's all done in the registration and discovery. Next one is configuration. Get to know your part. So I mean configuration of your senders and receivers. Here again, control software can query the capabilities of senders and receivers. What can you do? Can you do 8 channels? Can you do 2 channels? Can you do HD? Can you do 4K? It can query that, and actually the infrastructure does provide that information to the setup, to the control software. And as a next step, the software then basically tells the sender how many channels to do. It's all written there in the spec IS11, which already mentioned by Spencer. Then you have to set up the internal matrices of the devices. Again, there is a spec for that. And finally, don't forget, even ISO 5, which has been there for years, allows every sender to get a flexible multicast address. No, you don't have to set up the multicast addresses statically for your infrastructure. You can actually have your control software doing that. And it's already working widely. It's just that you have to ask the control software guys, please implement multicast management. So, and finally we connect. That's what we know already. The control software basically copy-pastes the transport file to a receiver. But it's important to know, the receivers then start to subscribe to the stream. There's nothing sent to a specific place. The guy says, hey, I want that guy. I want those packets. And then the network sends it to that receiver. So, and then again, it does update the registry and say, I am connected to that sender. In the registry, you have a reference for that. So the control software then can show, there's been a connection between these senders and receivers. And by the way, if you have multiple UIs, they will synchronize automatically because they all reference to the registry. You can have multiple UIs running in parallel and they will subscribe automatically to the updates. So the question is now, did that really happen? Did it really work? And the magic is, are the streams flowing? Are the packets flowing? Do I just see an updated patch point on my UI, or is it really happening? And that's where I think, after doing all this magic stuff, what we need, the next big step is a monitoring step. And that's why it's actually brand new. It's released now. It's called BCP 08. And in the monitoring side, that actually allows you the monitoring now, standardized monitoring now allows to basically check what's going on really. Down to packet level, down to PTP level, and so on and so on. How that works is this. So there is this new spec called BCP 008, and that's what you have to, as an end user, go to the manufacturers and say, do you do PCP 08? It's going to save a lot of your time and maybe your life. Not your life, but let's say your production, right? So basically, the control software in this case can query statuses of senders. That's you know, who is there, which supports BCP 08. And then it says, hey, tell me if something changes. So the control guy, which becomes the monitoring part, right, says, who can do PCP 08? The guys who can. I want to subscribe to any state changes you do. And then it basically, you can indicate that red, green, whatever state to the user interface. I'll tell you in more details how that works. And yes, you can query then more details, whatever. But the main thing is, you know, do you have everything you need? Are you okay? That's a very simplistic monitoring approach. And that's standardized now. So, let me introduce you to this BCP 08 very quickly, because I think it's so new that a lot of people don't know about it. Has been missing in your presentation as well. So, the BCP 08, the traffic light approach, the monitoring approach in a standardized way, basically says every sender and every receiver provides you a number of traffic lights. And the colors are kind of specified. It's green if everything's great. It's yellow if things are still okay, but there's some stuff happening, like you lost network B, but you still have A, that kind of stuff. And obviously red if something is really unhealthy and there's a real problem. Everyone understands traffic lights. So inside, what are actually the domains, as we call it, the reporting domains? Every sender and every receiver is feeding back to the world, to the control system and monitoring system. It's actually the overall state, which says I'm completely okay, whatever. And there are 4 what we call domain statuses. 4 traffic lights in every sender and 4 traffic lights in every receiver. Basically, 2 of them are checking connectivity. They say, I got all the links I expect, up and down or whatever, and the second one says, I got all the packets I need. Or maybe they are too late, whatever. That's another traffic light. That synchronization traffic light says, I got all the synchronization I need. And we keep it very open. If you only expect synchronization on network A, you are green, and if it's gone, it's red. But if you expect synchronization on A and B, then that would actually use the yellow state in the middle. And finally, you check whether you can decode the stream on the receiver, or a sender says, I got something to send. For instance, if there's no SDI connected, there's nothing to send there. So it's also a capability to monitor that. Now, all these traffic lights try to channel what the manufacturers most likely already have in their products. We don't force them to implement stuff they don't have, but we force them to report it in this way. So you guys get it back as a traffic light. Now the overall state, there's a spec saying it always has to take the worst state of all the members. And that guy you want to see on the UI straight, because showing you everything's cool. So I want to demo that. That's why I use a laptop. I'm not sure whether we have. Can I just try to hold in my hand? I have here reload. Hopefully that works. Yeah, it does. So there's a UI, a very simple UI. Some senders, receiver, and the top ones support BCP 08, the monitoring. You can already tell there's a green light on the sender side. If I connect the sender to a receiver, let me do that. You see a green light coming up on the receiver side as well. All cool. Now, that's a demo, right? But so I can fake some problems here. Let me take down a NIC 1 of a redundant device, right? If I do that, you immediately see that the traffic light turns orange. And it says there's something not quite right there. And as an operator, I see it's yellow, it's not red, right? Because if it's red, then I really have a problem. So if my UI allows the user to check the details, I can go in there and I see the 4 domains in there. In this case, because the NIC 1 is down, that influences packet loss and it influences synchronization as well. By the way, the texts here are twisted in the demo here. So basically, link 1 is down and there's a packet loss, of course, and I have also no sync on NIC 1. And I think that's already very, very intuitively clear what's going on. The packets are still okay, the stream decoding. So basically, on the sender side, it looks very similar. Links and synchronization is exactly the same. On that side, where we detect packet losses on the receiver side, the sender may report transmission errors. So you see, this is very generic. It's not bound to 2110. You could have SRT or whatever, where there's transmission errors. So that would be the traffic light for that. And on the fourth one, where we decode the stream on the receiver side, the sender could say, I don't have anything to transmit. For instance, there's no signal on SDI in 3. So that's a red state, right? Although it has nothing to do with my IP, but in practice, it's as much of a problem as it is to have a network issue, right? So in this case, the overall state would go red and say, no signal on SDI in 3. It basically takes the worst of all of them. So basically, that's what BCP08 is doing, and that's brand new, but it is as simplified as possible, both from the vendors and actually also from a UI perspective, so that overall state can then be mapped to the UI straight. And yes, by the way, there's a little counters, because if you forget to check and it's green, like it will be right now, there's a little one saying there was an incident before. So there's a little counter. It's not a logging, right? But it just says there was something happening. So logging is still the part of control systems and monitoring systems. But the end devices, they do what they do best in a very, very simple way. So what we do is basically we move some of the logic and intelligence into the edge devices, so they don't report stuff which you are not interested in. For instance, if the sender is disabled, the receiver is disabled, not connected, it shouldn't report packet loss, right? It doesn't, because that's as it's specified. So we put in some very simple practical rules for that in order to make your lives easier. Okay, I guess I want to leave you with some documents and links, which is maybe important and interesting to read. And now we are probably both open for questions. Thank you.
If you're going to ask any questions, if you could grab the mic off of the table there, just so we can capture it on the recording.
So I was quite interested. You mentioned multicast addressing is in ISO 5, as in assigning multicast addresses. Though I've yet to encounter that on a device I've ever used. And so I'm just wondering, because devices go ISO 5, but then I never find a tick box to say get the multicast from the NMOS registry. So is that a requirement of ISO 5 that they should be doing that if they've got the tick? If they've
Absolutely.
got okay.
It's something which is most likely there, but you don't know about it.
Right.
It's until you actually go there and assign a multicast address to that sender, you don't even know it's possible. So that's already in there from day one.
Yeah. Okay.
But you're right. Some vendors, in general terms, for instance, the registry is just possible to be discovered via typing in a manual IP address. But it's possible to do that via the DNS query. So what I probably advertise here is do it right, because it's already there. Don't go fancy, but that's already there. So multicast addresses, yes, absolutely, can be assigned and have to be assigned. Any compatible ISO 5 device has to be able to accept that assignment. You can test it if you use Riedel Explorer, right-click on a sender and they say go to stage mode, whatever, and then you type in a multicast address, see whether it changes.
Okay, thank you.
No tick box is needed. There's another question there.
In one network, will there always be only one registry, or can you have multiple registries and will it then detect between each other which one is best? Or
There is a specification for multiple registries. If you use DNS in order to find the registry, you can have multiple entries with priorities. So if one is not reachable, it goes to the second one. I should say, in practice, I wouldn't use that in that way, because if the end device then has to decide to go to secondary registry, it's supposed to stay there. If at that moment a new device comes online and the first one is back, it will register the first one. So you got some split brain. That's being acknowledged in the community, which is not a good situation. For now, the solution I would recommend is do a clustered version with one IP address everyone talks to, and behind that IP address you do a load balancer to switch between different registries. That's in practice how it works. The other one is kind of a bit of a dead thing today. To talk about yet to find a solution somewhere out in the market. So there is a conceptual problem even on that one, which I brought up. Yeah.
IPMX defines the behavior you should use in that scenario.
Yeah, okay. Behavior is clear, but there's a logical problem behind it. The behavior is clear, but you will still be able to get into that split brain situation, and that's a problem.
What IPMX has defined is once you're on a registry, you don't move off the registry until that is taken down. So if devices move to a backup registry, then a new main comes on, you have to take down the backup registry.
Okay, manually, right. Okay. Yep. With manual interaction, yeah, of course. You can just shut down the redundant one, and then everyone is forced back to main. Yeah, of course. Other questions? Yeah.
I do have one. What about facilities that tend...
Mike, maybe?
What do you do with facilities that tend to not want to use DHCP and have statically defined
You're already happy now, right? I mean, you can always type in stuff manually, but my thing is that let's move away from it. Let's try to move away from it because it's stable, it's there. IT does it for years. I had customers say, "Oh no, the DHCP," because what happens if it's not there? I asked the IT department, "Can you check the logs? How much downtime did you have in the last 5 years?" It was 0. They have brilliant redundancy options there. Let's start using it. My opinion. On that.
Mine as well.
Well, I'd like to thank everyone for taking the hour out of the ride and joining us today. And I'm sure that Stefan or Spencer would be happy to answer further questions for you. Let me get behind you here. There you go.
Okay, so this is about interoperability, and I'd always thought that interoperability was obviously a good thing until people in the AV world started asking, why do I want that? So I'm not expecting many people to have a revelation moment, but that's why we're doing that. Something that's going to nudge people into the, oh yeah, it's a good idea. Change it from a could have to a must have. As we go, keep in mind that if you're doing, unless you're doing a greenfield installation, interoperability is something that's going to happen step by step. It's going to build up, but it's got to be part of the master plan. Step by step is fine. As we all know, yeah, every journey starts with the first step, but this is a journey that's been walked before by SD2110, so this is nothing new. So we'll be travelling past the as we go through through Amsterdam, one of the foremost diamond centres in the world. And interoperability is a bit like a diamond. It's got multiple facets, so we're going to be looking at it from multiple perspectives. And they're all going to be in the context of IPMX, which is a suite of published standards, as you know, and open specifications, which have got interoperability at their very heart. And I like to think that that interoperability gives you options, even if you initially prefer to buy everything from whatever your favourite brand is. And the reason why, of course, is interoperability doesn't detract from that one trusted brand. It adds to it by giving you a degree of flexibility that you might not have in the so-called walled garden. Let's consider now the combinational possibilities of two devices, A and B. For either of those devices, there's going to be three compatibility outcomes. It works together with the other one. It works in isolation from the other one, and it doesn't work at all. And those outcomes lead us to four possible states of working. If they happily work together, they're going to be interoperating. If they work together, but not with in the case of the other one, they tolerate each other. And of course, if they don't work, then there's going to be interfering, and there's two of those possibilities. And the worst possible scenario, we won't even go there. So, what's that likely to mean to us in the real world? And we just need to look at 2110 to see what happens there, because there were a number of anecdotal issues where 2110 didn't seem to be interoperable, and the reality was, when you dug into them, people had perhaps adopted different bits of NMOS. Some had done 4 and only done 4 and didn't interoperate with the other ones, and that was putting it, of course, firmly into the not getting on with each other category. So too late from 2110, we learned that. And in IPMX, it's now mandatory to support both 4 and 5, and indeed 11. And so that's going to be encouraging the greeny blue behaviour there, rather than the yellow behaviour. And it's not just 2110. Here's some other examples. In CCTV environments, they found that some of the IP cameras adopted RTP, but tweaked the associated RTSP so that it was just enough to be different and need a different API. Their cameras worked with their software, and third parties had to do a tweak if it was going to work. They had to make their product super tolerant to work with the other ones. That's a lot of extra work to overcome a deliberate obstructive action, and it resulted in a movement called ONVIF, if you want to look it up on the web afterwards, one that focused on interoperability between devices. Closer to home, you might have seen product descriptions that mention a standard but have got some sort of trailing or leading word that modify it, so it's not quite. And there's a lot like that about. Perhaps they say, yeah, this is 2110, when they mean in reality it's their spin on 2110, which works in some before we get to considering compression, which is obviously at the heart of most of what we do. So For devices to be able to interoperate, they've obviously got to speak the same language. For example, use the same codec with the same feature set enabled at both ends. Because if one end's version 1.2 and the other one's version 1.3, they're clearly not going to all have the same features. So you've got to have that common understanding of the supported features. And if we widen our scope to include uncompressed as well, and let's add a little real-world complexity, let's say the receiving device needs to switch between uncompressed and compressed streams, then you're into a different environment. So we've got two UHD 60 content sources here. One, because of its application, needs to be perfect, and the other one doesn't need to be of the highest quality because that's fine, it's compressed. Both have got good reason to exist as they are. Now, it's one thing to be able to reboot a receiver and select a different mode, in reality using a different firmware. It's another thing entirely for the receiver to be configured to be happy with either stream and simply switch between them. That's the sort of interoperability we're looking for. Once the codecs and the connecting diverse devices are there, this is inherent interoperability at the device. But what if the receiver doesn't understand compressed? Can we still be interoperable? Now what we need to do, of course, is enable the interoperability with some sort of conversion gateway, something that's going to transcode or transform the data from, say, a JPEG XS camera into a format that an uncompressed only device, say a presentation switcher, is happy to receive. In that instance, of course, you've needed to take a stream that wasn't 25 gig and make it look like it belonged in a 25 gig stream. So here we've enabled interoperability using a network device, and that conversion gateway, I said device, it could be software, of course. Ideally, we'd want this conversion stage to be able to handle bulk conversion, multiple streams at the same time. Remember, I spoke about the stepwise path to interoperability. This is part of it. This is taking something that isn't interoperable and helping it along the way. But what if the networks were different? Then all of a sudden we've got a different sort of conversion in play. Network on the left here is 2110 using PTP with the SMPTE profile, and the one on the right is a lower cost network with either no PTP or the IPMX profile of PTP. Sources and receivers are all uncompressed here, so the devices at their level are already interoperable. But there's no diversity of devices here, of course, but the connecting networks are different. So we can create interoperability here at the network level now using a different conversion gateway. One half is in the PTP domain, the other half is in the non-SMPTE or even non-PTP domain. And in passing, note that if these are both uncompressed UHD 60, that isn't just a 2110 thing. That can exist in the AV world as well. So we've looked at inherent interoperability and enabled interoperability. Now we look at default interoperability, because this is a common one. In this instance, our blue encoder in room 1 is simply not, they both look blue there, they're simply not compatible with the green decoder in room 2. We could add a blue decoder and green encoder, as I've done there, at one end or the other, and a link at baseband. I've shown it as HDMI here. It could have been SDI, of course, or some other. This is default interoperability. It always works, but it comes with some drawbacks. And one is that it forces consecutive processing, compression after compression. And with the wrong codecs, that approach can quickly go wrong. With the right codecs, it's no problem. More obvious drawback is that you have more hardware in the rack. There are now 4 codec devices here to do a job that needs 2. Increased purchase costs, increased operation costs, increased points of failure, increased space use, increased spares holding, and so it goes. What are we saying? We're saying design for interoperability as far as the end user if you can. Keep the workflow in the network if you can. Scale. Now this applies if you've got diverse classes of equipment, diverse types of assets or rooms. Small scale is easy. For enterprise or wider, interoperability needs to be planned. I'm going to illustrate it using rooms here. Now if you're only concerned with a single room-sized deployment, then all the endpoints have got to do is talk to each other in the room, and that's pretty straightforward. The easiest way to do that, make them all the same brand. They now consider a building with lots of rooms or a campus with lots of buildings, and the scenario changes. Instead of isolated intra-room, you're now looking at dispersed inter-room communication. Those rooms need to talk to each other. Now, if the AV of the campus was developed as part of a master plan, interoperability is going to be baked in. It's the way it should be. But if each room was an independent project, then there's probably going to be a little more complexity, and the chances of them actually interoperating gets smaller. Assumptions. Now, there's a lot of assumptions in our industry. Planners in particular like to assume a steady state. Most people creating a project scope for the planners assume a steady state. The steady state assumption makes the planning simpler, but it doesn't recognise the nature of the world that we're all living in, and the management literature refers to that as VUCA: volatile, unpredictable, complex and ambiguous. That's what we've got to cope with. Another unsafe assumption: oh, we're never going to need to do that. And we all found from recent experience that not only did we need to do it, but we needed to do it in a hurry. You know the global events that I'm thinking of, it affected the world. And to be fair, we all did pretty well in managing that. And then everyone found themselves saying, well, we handled that pretty well. Now let's do it the way we would have done had we not been in a hurry. That's what they should have done in the first place. They didn't do it first around. They hadn't asked what might happen to force a change on us. They didn't ask enough what-if questions, and that's what I'm going to proceed on to now. Some what-if questions to illustrate where interoperability adds its value. Here's our first one. Some AV over IP systems assert that there's interoperability between brands based on the fact that they've got a common chip in the middle. Well, if it's our chip, of course there's going to be interoperability. The flaw in this line of thinking is that manufacturers add stuff around the outside of that chip, and what they add is different. So if they've added something different, you may well find that some of the features are interoperable, but not all of them. Here we've got the same heart, different surroundings. Now, it doesn't matter if the heart can support high dynamic range video if the elements around it can only support 8-bit. You see how it works. So brand A and brand B can't be interoperable beyond the features they share. Another what if. In our industry, there are some dominant brands, and they like to do it their way. They present the one-stop shop. You know, the ones that have got hundreds of products in their catalogue. And they encourage end users to see themselves in the way I described earlier as the brand X house. That's what we use because that's what we know. But we have to ask ourselves, do they really do everything? Or are we ultimately going to find that they can't cover all possibilities, and the day comes when we need to bring another brand in? And that's why the one-stop shop distributors carry multiple brands. They recognise that the big brand can't do everything. There's good reasons for standardisation, but instead of standardising on a brand, better idea is to standardise on a standard. That way changes of direction are not so painful. So, another what if. Now, when a brand stops, the Red Cross, if it's a proprietary line, it stops. If the follow-on product is not backwardly compatible, it's stopped. Worse, the compatibility system for the whole of your system that is using that system is now compromised. If you can't get more product, you've got 99 good products and one bad product, your capability has gone down. So, you might need to replace the whole system, not the one failed unit. That's and the capacity worsens every time another unit fails. If, however, another brand has got products that are interoperable with it, you've got some options. Let's illustrate that. So here we've added a different family of products. These two, yeah, they could have been bought at the same time. That one did the job, it was proprietary. That one would have done the same job, it was interoperable. No difference at the moment. The difference comes when you get to the end of the life. Because that bottom half was interoperable, you've now got choices of other products, perhaps that didn't exist on day one, that you can substitute in. And this is about the supportability not of the product, but of your system. Because the supportability of the system doesn't end until the last product ends. And that's a big difference. That gave you interoperability leading to supportability. There's good value in working with a manufacturer that's got long product lives. Both of them had that. There's extra value in working with one that's got interoperability. Another what if. What if a planned extension or a total replacement gets scaled back? Oh, we've had a bad quarter, budgets are frozen. Real life, huh? So the intended single brand plan unintentionally becomes a multi-brand environment because the replacement is not the same as the partially changing incumbent. How much heartache would have been saved and capability preserved if there'd been interoperability from the start? Another user what if. I'm showing an organisation here with different departments. You can see different coloured windows there. And they've ended up with a few different solutions, each right for their own needs. You might think about the bottom floors being, say, an ST2110 media hub and the balance being a bunch of different AV distribution systems. Mostly they've followed a corporate standard, except for a few different ones, the different specialised needs. And now management has asked two of those departments to work together. One or the other has got to replace what they've got because they didn't work together. If the corporate standard had allowed different sorts of users, this project might have been as simple as a button push. This is the scale thing that I mentioned earlier. Interestingly, the department's analysis also works in governments, where the departments, say justice and industry, might be totally unrelated, except at the higher levels of government. And if ministries change, now you want employment and pensions to work together, one of them's going to have to change. Would have been a whole lot better if they were interoperable. This image is the same as the last image because the kit is the same in this environment, but the what-if question's different. Something now has cropped up unexpectedly, rather than being a project that was planned for between the departments. Unexpected developments is almost always happens at the most inconvenient time when the project is about to go live. Quickest solution, borrow something from your neighbour. That works, of course, if your neighbour's got the same as you, and doesn't if they don't. The one thing you don't want to hear is, yes, of course I've got a spare encoder. Yes, you can have it now. Unfortunately, it's not going to work with your system. The logic of this slide and the last slide applies not only to departments in a single organisation, but to different organisations who themselves were thrown together at an event. So here we've got two similar corporates, probably good candidates for a merger, and there's a lot of that goes on in this industry. The AV hearts of the two enterprises are different. The AV over IP needs aligning. This is destined to be a cost of merger, just like merging the IT, unless interoperability happens. Now I bet you can all hear both of the AV managers in those organisations saying, not my job to plan for decisions in another organisation, not my budget, not my problem. Here's the thing, for one of those AV managers after the merger, it is going to be their problem. The what-ifs keep on coming. It's almost inevitable that plans change. Sometimes needs change. Sometimes they change during the planning phase. It's not unheard of it to change during the implementation phase. But it's much easier and quicker to handle the impact of the change if the system architect doesn't have to start again with a completely new system. If interoperability had been considered from the start with their network-based design, the platform and the core can stay the same, and a change of user needs is simply addressed. I mentioned global needs earlier. What ifs happen globally too. They can unravel the best of plans. We've all seen fires, earthquakes, tsunamis closing factories, ships stuck in canals, global pandemics stopping movement of components in and finished goods out. We know it happens. Without warning, you can't get what you wanted. ETA's gone out to 18 months. It happens. It's not the manufacturer's fault, but they can't deliver. Now, wouldn't you want interoperability with something that you actually could get? Of course you would. That's what keeps you in business. Another what if. What if there's a failure? When a tech goes out to a fault, they systematically work through the system to try and isolate it. And then they start substituting, first cables and then boxes. And it's much faster and easier to do that if you haven't got to find the exact same box. If you can use something from the same class that's interoperable with it. This interoperability is called design for support. It's a really good idea, and it comes with interoperability. So we've seen a lot of what ifs. And these considerations are not uncommon, and they're easily managed if interoperability exists. One final what if. What if they ask you for interoperability just after you've installed something that isn't? That one really hurts. So who benefits from interoperability? Well, it's everyone at the end of the day. I often hear the manufacturers won't do it. It disadvantages them. They want vendor lock-in. That protects them. ST2110 gives us 8 years of experience of the fact that manufacturers do work with each other and can make interoperability work. Why do they do it? They bring more products to market faster. They make more diverse products, not having to consider a new ecosystem every time. They can exploit volume for a larger market to develop for a smaller related market. The manufacturers can make complementary product without engaging in partnerships. And all of these other folks all benefit too. All right through to the channel. Who loses? It's the people who wanted to keep the system all for them. So if interoperability is seen to have immediate uses, it's part of the operational definition from the get-go, and the true value of it, of course, only becomes apparent later. It's then that the if-onlys and the we didn't expect observation are made and found to be true, but of no consolation. Nobody championed interoperability from the outset. Too late they realised it was important. As I've been talking, you've read their words. They're my words. Are they valid? Interoperability means options. It's a must-have that you don't need on day one. It's a should-have, but it's not a nice-to-have. Time for questions? I'll ask you one. Does anyone think interoperability is a bad idea? Thank you.
Thank you for keeping us on time, Rob.
So, very happy to be here. My presentation will be about codec options in IPMX and when you should use each option. So a quick introduction about IPMX. IPMX really aims at covering a wide set of devices. It's really designed from the get-go to be the Swiss knife for AV and production. And therefore, it needs to cover a wide range of use cases, and each of those use cases really put different constraints. And therefore, you have to design the specifications for those different use cases. So for example, in an IPMX network, you might find some professional production equipment, such as production switchers, cameras, but also some AV signal routing systems, so typically HDMI encoders and decoders, but also more IT-centric infrastructure. So it can be professional IT infrastructure, such as servers, but also more end-user IT infrastructure, such as laptops and workstations. And with all of those devices, you've got different specifications, and you've got to design the specifications so that you can implement IPMX on those devices. And within those devices, video is really the limiting factor. That's what puts the most constraints on the device. Because when it comes to routing and control, for example, as Rob said, NMOS is really a must-have and is really a simple solution in the sense that it's been deployed a lot and it doesn't take that much network bandwidth and doesn't take much processing power. Audio is also true for audio. Audio over IP has been there for a long time. It takes bandwidth, but not as much as what you have with video. Security, encryption, and the HDCP, these are all things where you can have a common solution with PP and HCAP in the case of IPMX. Same goes for remote control and KVM, where you can put USB over IP and you've basically covered the problem. However, with video, you have such a high data rate that is associated. So for example, when you've got a 4K 60 uncompressed feed, you have 12 gigabits of data per second. And that doesn't fit on an Ethernet cable. Like a Cat6e cable, Cat6 cable is 10 gig maximum. So that doesn't fit on any Ethernet cable, and so you have to go for fiber directly with more costly switches, for example, and you cannot go into more IT-centric devices. So you've got some really constraints that are posed with video. So what's the solution to this problem? Well, compression. But the thing is, with compression, it's impossible to find a perfect balance between the different, let's say, requirements that you have with codecs. So you cannot have a very low latency, a very high image fidelity, and a very low device complexity. That doesn't work together. So you kind of have to accept the trade-off and pick and choose based on what are your needs. And so for this reason, multiple video profiles have to be supported if you want IPMX to be the Swiss Army knife of AV. So a quick word about what a codec is, because I'm aware it's pretty specific. Well, the basic idea is that you want to remove any unnecessary data while maintaining the necessary information. So the way it works is that you take some input, you remove what is unnecessary, that's your encode phase, and then you've got the decode phase where you have to get back to that original format that you can actually use. And so how does it work? Well, you have three main stages. The first is decorrelation, where you find and remove redundancies. So that stage is lossless. You can revert back to the original if you only stick to that stage. So if, for example, if you've got a red pixel and another red pixel right nearby, then you can just send the information once and not twice. Then you've got the step of quantization. That's the lossy part. This is where you remove noise and any unnecessary data. So let's say you've got data that is not visible to the naked eye. You can just remove it and the audience won't notice. And then this last stage is entropy coding, where you assign variable length code depending on how frequent certain data is. So for example, for very frequent data, you will assign a shorter bit length because it's more common, and for less common data, you will assign a longer bit length. And for all of those stages, you've got several compression granularities that are possible. You can look for redundancies within part of a frame, you can look for redundancies within a whole frame, and you can look also for redundancies between frames. And you kind of have to find, there's a cutoff, so you have to decide where you stop looking for redundancies and you start encoding the data. And that cutoff is at the heart of any codec algorithm. So this is part of the work that the Video Services Forum has done. And, there has been an assessment of what are the different categories of codec that are available and what are the technical differences between those. And so based on this report, this is AIMS has defined several video profiles for IPMX. And so we've got first the uncompressed video type, where you really send only raw pixel data information, and therefore you don't add any latency. As soon as you receive a pixel, you start encoding it and you send it over the network or you store it. Then you've got some intra-frame codec, which can be subframe or frame-based. And so if it's subframe, the way it works is that you only wait for a few lines of data to start encoding. And therefore, since video works in a rasterizer method, you can just wait for a given number of lines, and once you've received those lines, you can start encoding and sending it over the network. And so you maintain very low latency at the encoding phase and the decoding phase. And so those types of codecs, such as the standard JPEG XS, are spatial codecs, so they don't use any temporal correlation to encode. So therefore, all of the information is contained and independent from one frame to another. Then you've got some interframe codec with a predictive mechanism, where you will use information from previous frames to determine what's the information of the frames that follow. So you can work on the frame basis, but also on a subframe basis there. And if you work on a subframe basis, you've gained a huge amount of quality because you can reuse information from previous frame without adding any latency, because you can still be reusing data from the previous frame that you've stored. And so this category of codec is great for content where you have fine details and where quality will build up over time, and therefore it's really mathematically lossless in those static areas at the end after several frames. And so one example is the TDC mode of JPEG XS. And then finally, we've got the interframe types of codecs, so AVC, HEVC, for example. And those codecs look at redundancies across several frames, frames that come before and frames that come after. And that means that you have to wait for those frames to come to start encode and decode. And mechanically, you've added latency because you need to buffer several frames before you can actually store them or send them over the network. And so that means that with those, with these categories, the area of redundancy grows, and therefore you're able to compress more. But since the cutoff, let's say, comes later, you've added more latency. And so that's the trade-off you have. The more you compress, the higher the latency. And so, based on this report, Ames has really defined 4 video profiles that really target the different use cases that IPMX aims at solving. And so you've got first the uncompressed video profile, which is based on SMPTE 2110-20, which is very common. Then the JPEG XS video profile, the HEVC video profile, and the AVC video profile. And the VSF TR10 document themselves don't specify a specific codec, but since IPMX is about interoperability in practice and not in theory, Ames has decided to select a few of those codecs and to let's say, stamp them as official profiles. And so if you want to implement an IPMX product, there's a set of basic requirements, but you don't have to pick a specific profile, but you need to pick at least one of them to be IPMX certified. So it can be the audio profile, but also any of the video profile. And crucially, all of those codecs that are selected are all non-proprietary and standardized either at JPEG or MPEG, and that's great for to make them future-proof. So I want to go into a little bit more details about each profile. So first, the uncompressed video profile. Where should you use them? Well, you should use them within IPMX anywhere where you need compatibility with SMPTE 2110-20 production equipment. And so it's great because you don't have any added latency that is due to the compression algorithm. In practice, you've got latency due to the capture and the rendering and the network infrastructure, but you have no latency due to the codec itself. And also, using this profile is great if you want to have frame accurate switching, because all of the information is contained within a specific frame, so you don't need to wait for a few frames before you can switch between streams, for example. And so it's great if you want to interface with high-end broadcaster-grade studios, for example, or if you want to distribute in bandwidth-constrained AV environments. And even one thing to consider, though, is even if your network is sized for uncompressed video, the simple fact that you've got such a high data rate on devices means that you cannot have this profile in any kind of device. For example, you will never be able to receive an uncompressed video stream on a standard laptop. And that's where the other video profiles come in. And so you've got first the JPEG XS video profile, and it's a great video profile if you want to be compatible with SMPTE 2110-22 production equipment and contribution equipment as well. So it also enables frame-by-frame access, because information is self-contained within a group of lines and not across frames. So that's great if you want to do some switching, instantaneous switching. And so you can use that profile if you want to interface in local area networks, Also in wide area networks where TRO8 is being used. That's a specification for JPEG XS within 702110. And also in cloud-based workflow where JPEG XS is used as an ingress or as an egress. It can also be used in post-production workflows and any live event distribution where you need synchronization and where you've got latency constraints, such as image magnification, for example. Then I want to talk more about the TDC mode of JPEG XS. That's not a profile, but a profile mode, which is an extension. So it's not mandatory if you adopt the JPEG XS profile, but it brings additional functionalities. This mode brings an additional 50% improvement in compression, where and especially on static type of content. So think of Excel spreadsheets, PowerPoint presentation. This kind of content works great with this mode of JPEG XS. And really, it's been designed if you want to fit a 4K 60 content on a 1 gig link, or an 8K 60 content on a 2.5 gig link. That is the codec you would go for if you want to target those use cases. Then we've got the HEVC video profile, which is great if you've got bandwidth constrained environment and where latency is less critical. So here, compared to the TDC profile of JPEG XS, the algorithm will look for motion between images and not for lack of motion. That means it's great if you want to have some natural content that you want to distribute, but if you've got static content where you've got fine details, it might be less suitable. And here the paradigm is really, okay, let's maximize compression at the expense of latency and algorithmic complexity. What I mean with algorithmic complexity is that it's very hard to implement in software, and the way you would implement this is using existing SoCs that have hardware encoded capabilities to decode and encode this codec. So some of the use cases include, for example, products where you have bandwidth constrained endpoints. So for example, if manufacturers want to turn an existing display into an AV over IP endpoint with IPMX, then you've got a very small network interface that isn't able to fit a high bandwidth. So therefore, you would go for that kind of codec. And as I said, for less latency critical AV distribution, or for example, for UC devices which have very simple chips in it, and with hard-coded capabilities for H.265, for example. Then we've got the H.264 video profile, which is H.264 solved the same use case as HEVC, but it's a previous generation codec. The reason why it has been adopted in IPMX is that it's really the lingua franca codec on all SoC platforms, on all chips, really. And therefore, you're able to leverage any kind of device that have this accelerated capability. And on those devices, often you don't have enough processing power to go for other options. And so that means that it's therefore the only viable option to turn those devices into an IPMX endpoint. So a quick word about some workflow examples of where the codec and profiles would be suitable. So the first scenario is, let's say you have a mixed production and AV distribution workflow in a corporate space. You've got a large production facility with existing 702110 equipment, and you've got, for example, a boardroom, and you want to distribute some content in a theater where you're performing, for example, image magnification. Well, in the large production facility, since you've got already 702110-20 equipment, you would probably go for the uncompressed video profile. Cameras, you might be constrained by your existing net JPEG XS is very suitable if you've produced in your production facility. You might also want to make sure that content has a very low latency, and also that it fits on a 1 gig link, for example. And therefore, a good choice there would be the TDC profile of JPEG XS, because you would be able to fit that 4K 60 content on that 1 gig link, and while making sure that there's no latency that would make the experience uncomfortable. The second scenario is on the other hand is a scenario where latency is less critical, or where you have a bandwidth constrained environment. There, you could have, for example, a small production. You have more affordable bandwidth in that part of your facility, as well in your NetC or AVC feeds. And so between the two, you've got a whole range of use cases where you can mix and match based on what suits better for you. And what needs to be kept in mind is, in all of those scenarios, you've got a diminishing bandwidth, an increasing latency, and diminishing quality in general. Depends on the content, but that's what you would observe the further right you go. So, in conclusion, why do the profile help IPMX become a reality? Well, those profiles really serve as the basis for interoperability during vendor plugfest, but also on-the-ground deployments. So one example is in April, there was an IPMX tested event in Burbank at the Everts facility, and those profiles were tested on the field that served as the basis layer for interoperability. And so the audio profile, the uncompressed profile, and the JPEG XS profile were all tested. And so those profiles really enable to expand the adoption of IPMX across new industries and new use cases. Thank you. Do you have any questions?
Well done, speakers. Well done.
Thank you, Tina.
prepared for that. The boat might turn around several times, actually. When it stops turning around, I'm done.
I downloaded it this morning at like 7 a.m. So.
I'm sorry. Yeah, I saw it was only a small mistake by today. That's great. So we'll just swap my script turnaround.
When the boat turns around, that's when he's supposed to like be wrapping up, and then he'll hand off the mic. And the mic doesn't amplify; it just captures the voice.
Oh, I thought there's a big PA system on the rooftops. No.
Yeah, I was with John. John went first, I think.
Oh, is that what it is?
I followed John. Yeah. So.
Well, I'm sorry you have to follow up.
And
I should make Andreas go loud.
I can't see the notes, right? That's no, that's why I printed them. Yeah, this is a brand new one, and didn't have much time to practice. Yeah. So how are you?
Yeah, good.
Good.
Good show. The shift is starting to move from my side of well, the machine from real-time transport more to file stuff, more away from infrastructure to cloud, trying to solve the cloud problems. And also trying to get, now that we've got an ecosystem, we've got a number of partners trying to organize that whole thing. We've been trying to work with the EBU to try and form a kind of working group.
Okay. Yeah.
The EBU is going through some changes that are very difficult.
This AES work group is still, somehow open or stalled or paused. I don't know. We wanted to wait for the -42 stuff to be ready, and then they wanted to do it within AES as well. So Kent was on it, but I suppose won't go on. But
I know for a fact that our speakers need all of the time at a whole hour, so we're going to go ahead and get started. Thank you so much for attending the IP Showcase on the Water. For those of you who do not know who I am, I'm Tina Lipscomb, and I am the operations manager for AIMS, AMWA, and BSF. And on behalf of all three organizations, I'd like to welcome you and thank you for taking time out of the ride. We'll have you back in exactly 1 hour. And we have two great speakers for you guys today. We also have a crew who is helping us out. That's our host, and that's Faye and Nora. Don't know why I totally forgot her name. And our captain, Martin. And she'll be keeping us on time today. So if you have any questions, don't hesitate to ask. The toilet is not working.
Alrighty, that's it. Go ahead. Okay. My name is Andreas. I'm working with Lavo on the Ravenna topic. I bet everyone has heard about Ravenna. If not, it's something similar to AS67 and 2110, and I'm used to give similar presentations each and every year at whatever occasion. And I thought this year I will do it a bit differently. So you can expect a story about how these boats operate on this wonderful Amsterdam canal network. So it's all about aligning flows and channels while floating through the Amsterdam canals. And hope at the end you know how this and maybe AP networks will work. So here's the Amsterdam canal network. And of course on the canal network there are lots of boats, right? And that is us, right? Well, that has been us last year, but that's us. We are right somewhere. Where are we? We are here. That's where we are, and we are leaving the Rye port right now. Well, we will most likely take a route on the Amsterdam canals, as you can see. Well, I don't know if that's the actual route. And well, and on the return route, it will be James' turn to actually entertain you. And if I need more time than actually planned, we will make a few extra rounds over here until I'm finished, right? Okay, so looking at the network, a little bit more enlarged here, you can see that there are smaller and larger canals. So we have these fast Ethernet links, canals. We have gigabit canals. We have even more power, 10 gigabit backbones there. We have 2 of them and they need a link. Unfortunately, there's just a gigabit link between the 2 10 gigabit links. But a real huge network also has even more than 10 gigabit links, and that's where we have well, was it Rhine, part of the Rhine, the Amstel, I don't know. So that's a 100 gigabit link over there, and of course we have to have a link up to this. So they are all nicely linked, but with different, they can also flow faster through the bridges. Well, actually, they are not flowing faster, but you can, at the same time frame, you can accommodate more boats under a bridge, right? So, but the problem is, of course, if you use small boats, they eat up more of the available bandwidth because every boat needs, some common resources like a hull, a captain, and even much more. And every boat needs that, right? So you're wasting a lot of bandwidth with the small boats, although they're really nicer to travel with, right? And well, the large boats, in contrast, can accommodate much more people aboard, and they only have one captain and one hull, and so the bandwidth utilization per passenger is much better on those large boats, right? And ugly jumbo frames, they don't even pass through those bridges, they just don't fit, so they are not allowed here. Right? You won't see those jumbo frames on the canals. Occasionally you will see large boats, small boats, there are large boats, small boats coming up as well. So that's the way, and you just need to understand the larger the boat, the better the bandwidth utilization, the smaller the boat, the more boats you can accommodate on any given link. But it requires more bandwidth compared to the passengers. Now let's look at flows. Flows basically are a sequence of boats. So if you have our route and when there are some boats and they have the same starting point, the same destination point, so you can consider them a flow of boats, same start, same destination. And again, there are many different flows on the canal system, and part of these flows apparently utilize the same canals, the same infrastructure. And the problem is, as you can see, there are a lot of different routes, and some use the same links, same canals. And the problem is there's a maximum number of boats which can actually pass through any given link, right? Small canals, fast Ethernet, less boats, large canals, many boats, even large boats, right? Yeah, so we have these canal limits, and of course, if you're going back to this, big backbone here, that can accommodate a lot of different flows, a lot of different boats. But sometimes it's not possible to manage these flows to actually, make a good utilization of the available bandwidth. Sometimes boats get stuck, Yeah, because there is not enough bandwidth to feed all these boats through to the bridges. And that causes, at best, some delays, depending on the traffic, some varying delays. So, and in networks we call this the packet delay variation, right? And sometimes it happens that some boats just will be denied to pass the bridge at all. On networks, the packets will just be dropped. On the canals, we can't sink those boats because there are already enough bicycles in the canals. So at some point in time, they need to find another strategy. But that is actually what can happen on a network as well. All right, so that is the network, the links, the flows and everything. And now let's look at how the boats are actually packetized, boarded, how the people are loaded into the boats. You can see there's a boat, there's a line, and that's what it actually is. Here's our boat, here's our single line of passengers, and these passengers are nicely accommodated into the boat, one after the other. So if they would have been numbered, they just get their seat numbers assigned according to how they line up on the queue, right? Well, there's another strategy. It takes time, by the way, to load the boat because it's just one passenger after the other, and it apparently takes time to load the boat with this strategy, right? There's another way of loading the boat, and that is by multiple lines. So let's say these are Spanish, German, French guys, whatever, and you can load the boat one by one or nearly in parallel from the different lines. And then they are seated like, okay, the first one, you know, from each line, and the second one from each line. So they are seated in an interleaved way in the boat, right? And that means you can basically load more passengers in the same time frame. So although the boats are larger, they have the same packet time as the smaller boats with just from a single line, right? Yeah. Again, the summary basically is we have small boats which accommodate just a few passengers. They have what we call a smaller packet time, right? And these are just 8, and the packet time is 167. Very unusual packet time on networks, but well, hey, that's possible. And then we have the larger boats. They can accommodate more passengers, and we have 24 here. That's a packet time of 500 milliseconds. So that boat is ready faster. It can leave the port faster than the other one because it takes more time to load that boat, right? And yeah, with the strategy of loading from 3 different lines, we have the same passenger load as from the single line over here, but the packet time is shorter because they are loaded like 8 per line, which takes the same time than just 8 from a single line because they're loaded in parallel, right? So larger boat, but smaller packet time by just using multiple lines. Well, and of course, larger boats, as we know, good efficiency. We only have one hull, one captain, not so much overhead, good bandwidth utilization. Right, so, well, these boats somehow start, float around. Just have a look, it's wonderful out there. But at some point, they actually reach their destination. Oh, packet time, yes, I forgot that. Well, in order to accommodate the same amount with one boat, you need like 3 boats from here. And that explains why we have not as good bandwidth utilization. So at one point in time, the boats reach their destination. And passengers disembark. Not really much to say here, right? Well, what happens is the boat arrives, they get unloaded, and then they are allowed to leave one by one to the exit. Just as they have boarded, they are leaving the boat from the gate, right? That's the principle of unloading the passengers with a single flow. Now, how does that look with if we have multiple channels or multiple speaking passengers in one boat? Remember, we had 3 different rows loading, and now, of course, well, say English, German, Spanish, we can unload these lines. And since this is done in parallel as well, you can see these lines are nicely forming here. Now, if you want to squeeze them to the single exit, it might be a bit difficult. And well, generally speaking, what happens on a real network basically is you have a multi-channel multicast stream, or stream audio stream. It doesn't mean to have multicast audio stream, and there's the speaker only one stream interested in playing that back, and the others don't care, right? So what we have is a policing officer here, and he says, okay, all the Spanish-speaking people are allowed to leave and go to the exit, and we don't need the others, right? So what happens to the others? Well, bad things actually happen, and I hope they won't happen here in the Amsterdam canals. Or actually, that is the reason why this whole loading from multiple lines and disembarking into multiple lines is not very applicable to the Amsterdam canal travel or canal journeys, right? So yeah, we definitely want to avoid this, but in networks, that's what's happened everywhere, day by day. Just things get dropped which are not being used, right? Okay, that's how we unload the multi-channel flows. Now, next thing is, here's our canal network again. And usually, the flows start from somewhere and reach a destination. That is what we in networks are calling a unicast flow, right? We have a starting point, we have a destination point, the boat goes through the network, to the canals, and reaches destination. Well, if you want to send passengers to different locations, you will have to send them off multiple times to reach their various destinations. That's how it works here on the Amsterdam canals, right? Well, and that's where the concept of the magic bridges comes into life, because that's not very efficient, because you see 3 times people need to utilize these canal section, right? And that's where the magic bridges come into game. Here are the magic bridges, right? And let's say we apply one of those magic bridges right here. So what actually happens is this magic bridge is able to duplicate boats. Isn't that fascinating? Well, so that means in order for these 2 routes, they don't have to be sent off from the starting point. It's just sent off once, and the bridges know, okay, I need them once here, and I need them over here, right? So it's just duplicating these boats, and 1 boat is leaving here, and 3 boats coming out of that magic bridge. And of course, if we apply another magic bridge and another strategic point, we get rid of yet another flow. And so finally, all the links are only running 1 flow per link, right? And we don't have to have multi-flows just because we want to reach multiple destinations. The magic bridges, you know what that is in networks? That's multicasting. And the problem is actually, with multicasting and the Amsterdam canals, that only works if a magic bridge knows what destination the boat actually has to go to. If there is no destination for that boat, the magic bridge will just do this. It will sink the boat. Again, another reason why this is not very applicable to the Amsterdam canals, because of all the bicycles already in here, right? So we won't have this. So that principle does not really work here in Amsterdam. And of course, there would be much more to say about how these magic bridges actually work and how they know where the boats are going to and so on. But that is a story for another boat ride, and will certainly not fit into the point where we're making the loops before James can then take over. All right, maybe next year I tell you more about the magic bridges then. Yes. Right, okay. That's an important aspect in networks and not very applicable to the Amsterdam canals. But Another thing is the tour scheduling, or we would basically call it the alignment, right? And tour scheduling. So what we need for tour scheduling is basically a clock, a reference clock. That's our reference clock, and the way it works is that reference clock is available at all the starting and destination points. So they all run the same cuckoo clock with the same time. So they are all in sync with each other. And now, how do these clocks know what time it is? Well, there is a magic protocol, magic boats running on the Amsterdam canals actually. So there is one of these is the Zentralstation, it's the master clock. That's where the Swiss time from, well, is transmitted. And this one is transporting the time with very, very small, tiny boats. As you can see, they even flow in the different direction, right? And they utilize the magic bridges as well, right? So it's distributed to the other clocks and they are fully synchronized. That's the PTP protocol, by the way. Right. Yeah. Again, how does PTP really work? Yet another story for yet another boat ride. But just recall, small, tiny packets, utilizing multicast, making sure that all the clocks in the network are synchronized. Now, how is that applied for the embarkation point where people start? Well, we have that clock, you know, nicely ticking. We have that line, and so people are lined up, synchronized to the clock, and the first passenger in line receives a time. Actually, it doesn't receive a time. In our application, it receives a number. It's a clock cycle counter. I mean, it's just a number. It's a sequential number, and every passenger has the next incremental number assigned to him. So once the boat arrives, it will be boarded, and it's the first passenger in line who hands his number over to our nice captain. The others just board and drop their, you know, numbers somewhere in the water or in a waste paper basket, I don't know. But it's important that the first passenger hands over his number to the captain, right? So the boat leaves, and the boat arrives at the disembarkation point. Here's our number from the first passengers. All the other passengers are seated, you know, in a row, sequential. And the line forms. And that card is handed over to the disembarkation officer. And, well, basically, the disembarkation officer has an intercom. He knows from the master of disaster at what particular time people are actually allowed to move on to the exit. So here's the same clock, and he has magic information, you know, through intercom or whatever, when are people allowed to actually leave. So they have to queue up here again, and then once it's time, they leave at the same, you know, synchronized to the clock, they leave and reach the exit. And that is the principle of, oops, sorry, that's another one coming up. Well, this one actually, yes. That's the principle of the link offset. So we have the boat leaving and the boat arriving. We have the synchronized clocks. And that is the point in time when people are assigned their time cards. They travel through the canals, they reach the destination. And that is the administrative number or time the disembarkation officer has been told when are people allowed to actually leave. And then make sure that people are just leaving to the exit synchronized to the time. And so the two things this reference time actually does is it's the synchronization of the clock so that the frequency people are allowed to enter a boat and to exit a boat towards the exit. And it's the number, the time reference through a number which is sent over to the disembarkation officer to, again with the time, the information, what the total link offset should be. And so that's where people nicely exit a given ride at a very, very precise time from start to end. That's the link offset, right? Well, if the boat arrives a bit earlier, what happens? People have to wait a bit longer in line. What happens if the boat arrives too late? Well, the passengers are dropped again because there's no use for them anymore. Because if they are too late, they are too late. The next are already coming after them, right? Okay. Multiple flows. How does it work with multi-flows? Well, if we have multiple, single-channel flows which are moved into individual boats, it's the same principle. They all have the same reference. They all have the same clocking frequency, and the link offset is sent over to the disembarkation officers, and they make sure that everyone who arrives here is actually forwarded to the exit at the very same time, at the very same link offset. Even if one of the boats arrives a little bit later or the other a little bit earlier, they just have to wait a little bit more or less, and then it's tuck, number one, go ahead. Number two, go ahead, right? That's how the link offset works with multiple flows. That's how multiple flows are actually aligned. Left channel from one device, right channel, the other device, traveling one route, the other traveling another route. And at the destination point, they all aligned with this magic time card from the first passenger on the boat. Okay. So that is basically how AES-67 2110 operate and work. We have these synchronized clocks here. And now it comes down to IPMX. Everyone has heard about IPMX, maybe. It's the IP Media Experience, which is more targeting the Pro AV side of things. And they build upon the basis of AES-67 and 2110. But they discovered that they probably do not need this tight synchronization each and every time. Actually, most of the times they don't need this tight synchronization in their application scenario. And also, the principle of allowing passengers to enter the boats in a synchronized manner at the same time is also something which is not very popular in Pro AV, because think of an HDMI input that's running fully asynchronous, and people don't care if the next HDMI input or the next device has the same frequency, but they care that upon disembarking, about exiting the boat, they exit at the same rate they have entered the boat, right? Because you don't want to play out faster than people arrive, or slower, and then people again have to be dropped, right? And so IPMX has the requirement that the whole system also works without our magic clocks. And that is the point. When the magic clocks are not there, there is no given link offset anymore because we don't have a time reference. And there's also no common media clocking on the sender and receiver or all participating devices anymore as well. So how we do this? Well, we do this by observing how the passengers arrive at the embarkation station and then drive that as our media clock, basically. So it's observing how are the passengers coming in. We assume they are coming in at a regular interval anyway, right? And so that is our media clock on the inside. And of course, on the receiving point, we have a media clock as well, which needs to be the same as the one which was running on the input stage. But we don't have the reference clock anymore. How does it work? Well, there's another protocol which is the helper here. It's called the RTCP protocol, which helps the disembarkation point to synchronize closely enough to the clock on the embarkation point. That is how it works with IPMX. So the basic difference is in a fully synchronized AES-67 2110 network, we always have a common reference clock in the network. And with IPMX, we don't need that necessarily. We can run streams just asynchronously, that's the keyword on the network, but they cannot be aligned with respect to each other anymore. And they are not playing out nicely synchronized. They play out as they enter, like they enter the network. That is the big difference between AES-67 2110 and IPMX. And that basically concludes my little presentation about the boats on the Amsterdam canals and how all this routing and tour scheduling works. And I think, you see, I don't need any extra rounds.
Uh-huh.
Huh?
Well, the boat turned around like 5 minutes ago.
Oh.
You're doing good.
Right, thank you very much. Thank you very much, Ames, for having me back for a second installment. It's great to be here. Unfortunately, there's going to be no magic boats or bridges. In fact, there's going to be no non-magic boats or bridges. I would have loved to have put a sailboat. I'm kind of partial to sailboats, but on it, but alas, no. So, that's it. Right. So last time I really talked about 2110-41, which was the new SMPTE standard introducing a way to transfer metadata over real-time network. And that we've done trials with that. As things have gone on, things have matured, and people are looking at putting complete systems together. And we're looking at trying to see, okay, you need more than just real-time protocol to make next generation audio and high definition video work using dynamic metadata to enable those features. So what else do we need? Okay. So if you look at broadcasters and pay TV operators and the kind of evolution that they've gone through, they've probably started with a traditional workflow up here. Then VOD's come along, they've had a new VOD workflow, which is separate, that they've introduced. And then they've thought, hey, there's a lot of redundancy here. We want to try and consolidate our...
I think it says it's going to switch off in a few seconds. I think.
Right. So they've tried to optimize their operations, merged in their traditional with VOD, and that's great. And they want to do next generation audio, so immersive, personalized, accessible features. So they're going to need IP to do that, and that's great because we've got 2110 with the suite of standards that can support all of that. But the problem comes is how do we store things on the media server for play out or for encoding over VOD? So that's what we're looking at today. And pay TV operators and broadcasters are in a kind of tough position, like harder than, say, a VOD provider, because they're getting content from lots of different places, and also they're having to distribute in lots of different formats. And you've got this kind of end-by-end problem where you have to do loads of conversions. And generally this is solved with a house format or repository format. So this is not new here. People have done that for a long time. And OP1A, SMPTE OP1A, you're probably familiar with. If you on the file-based side, it's been around for a long time. AS11, which is used in the UK, is a derived version of OP1A. It's basically videotape, but in file-based form. Okay, it can sit on a server and be played out. So this is a kind of starting point for trying to solve this problem. The question is, how can we do this for including HDR, support HDR video and next generation audio? So this is the problem we were trying to solve. It's really reusing everything that we have with MXF, OP1A, but just finding new ways to support the extra data, metadata that's required, and making sure that we've got all the standards and specifications in place in order to do that. And it's kind of important that the metadata be contained within the file because it's closely associated with the content itself. If you tried to do it another way and doing like sidecar stuff, you just end up having to do lots of things which is not really standardized. So, so starting right at the beginning of the workflow where you've got content coming from the studio, well, how would you do that? So IMF, the interoperable master format, is a great way to solve this problem because a lot of standardization has been done with formats that carry exactly what we need. So we've got ISXD, which is a way of carrying generic XML, but we can use that for carrying dynamic video metadata, which is needed for HDR.
Headset's going to switch off in 1 minute.
Yeah, we've
Don't
got a
press the
warning on the screen, which is kind of in Dutch. And also for audio side, the audio metadata, we have ways of carrying ADM, serialized ADM, which could handle the next generation audio stuff, and also IAB, that stands for immersive audio bitstream. That's kind of like format for Dolby Atmos in a post-produced piece of content, which would be mostly for VOD kind of delivery. Okay, so on the live side, it's a little bit different because you don't have the authoring typically upstream. It may be done back in the facility. Certainly for video, it's actually the video metadata authoring is done at the same time as encoding. So typically what would happen is asset would be captured as it's live, you create a file asset, and then your authoring would be done off stream, kind of offline. You then create your repository file asset offline, which could then go on a server and be played back at a later time. Serial ADM authoring could be done upstream or it could be done at the facility. As long as you know what it is that's coming in, it means then that your mixer can't change things on the fly. Things are more static. Okay, so with this repository file, there's kind of two options that you have, or configurations that it's worth talking about. There's this, what we call same house and playout format, where you have a single repository file, and you're using that both for VOD encoding and for linear playout. So the advantage of this is that you only have the one file that you've got to QC. The disadvantage is you may need to do some conversions on linear playout that have to happen in real time, and so there's only so much you can do in real time. That kind of constrains you a little bit. So maybe there may be some quality compromises with that approach, but it's optimized for QC. So this approach, using two repository files, you've got more QC now because you've got two files you've got to run through your QC system, but you can optimize one for VOD delivery, so that would typically be in the kind of original frame rate, and then convert to a frame rate which is ideal for playout. So you may be going from 24, say, that you would get from studio to 50, which is what would be used for playout. But you can do that conversion offline. So you've got plenty of time to do that, and you don't need to worry about the real-time aspects. So, but you've got to do more QC. So, okay, now just quickly, I'm going to talk about what ISXD and serialized ADM, because these are the two new components to enable HDR with dynamic metadata plus next-generation audio. Essentially, all these are XML documents which are sent repeatedly over time, in real time, into whatever container it is, maybe with some optional compression. The compression really only applies to the serialized ADM. There actually is no mechanism at the moment for compressing ISXD on the video side. So ISXD, it's actually not specific to video. It could be any metadata in XML form. There is no registry as such that you have to like sign up and get your number. There is, on the MXF side, for the 2110, we did have to apply for a data type, which we have. We have a provisional one, which is here. In the coming months, that will be published by SMPTE, so that's kind of a guaranteed way of like identifying, okay, this is ISXD metadata that's being carried across on a 2110 network. Okay. So this is being used for Dolby Vision, but this is not a Dolby thing. Other systems using dynamic metadata like HDR10 Plus could equally use this. It's open for anyone to use. The format of the metadata and the contents of it are not defined in the standards. That's kind of opaque. Okay, so serialized ADM. So I presented on this kind of last year. It's been around for quite some time now. There's two versions of it, an ADM, which is a file-based version, and a serialized ADM, which is the real-time version. Dolby Atmos in post-production uses ADM for the ADM master, so it's very ubiquitous. And it's supported and standardized in all the major containers. So it is really the way to describe audio going forward. So it has some compression for bandwidth limited containers. Not really applicable to IP, but it's useful for SDI. And one other format that we needed, Dolby E is a legacy audio format. It's 20 years, but a lot of organizations have big libraries of Dolby E, and they're looking at moving to use ADM and serialized ADM, and they have requested a way of carrying the Dolby E metadata across the network or storing it in files without having to actually have the Dolby E bit stream and deal with the decoding and all the rest of it. So this provides a solution for that. It's not something we're licensing. It's publicly available. There is code on GitHub to do it. All the information that you need to do it or to implement it is freely available. There's no licensing program associated with this. Okay. So we've now got a kind of small ecosystem of kind of first generation products based around this repository file. And these are the kind of the folks here that are involved. So you can go and talk to any of them. They have about it. I know BeBright particularly have demos on the UHD forum booth. They have a really interesting demo. That's a good one to catch in Hall 14, I think that is. And also, I've put a whole bunch of information about the repository file online for you to have a look at. At the moment, we have some, I would say, high-level information plus various pieces of example code that you can kind of use to get going, like muxers, demuxers, conversion code, and so on. Okay, so in terms of case studies, and right, who's actually using this in reality? Canal Plus are the first organization, and they were really kind to let us talk about this and publicly. They've really been our partners in trying to solve this problem, but solve it in a kind of real world way. And they're up and going now with VOD, and they're doing linear trials at the moment. On the ingest side with Canal Plus, we've got the Marquise products, which are used normally for generating the repository file. The exception to that would be for Dolby E. Emotion Systems has a long history of dealing with Dolby E in the file world, so they were kind of an ideal partner to then do the conversion between Dolby E and the ADM representation of Dolby E. So that is something that they've kind of taken on. And they're at the booth as well, at the show as well. On the playout side, Canal Plus decided to take the single repository file approach. And for VOD encoding, they use a Dolby service, Dolby Hybrid, for that. And on the playout side, we have the actual playout itself is done by BeBright. There's audio processing by Younger. We actually have a couple of Younger colleagues here as well, so you can ask them more details about exactly what they do, the manipulation of the audio and the metadata. That's all done in real time. It doesn't deal with the repository file itself directly, but it could be processing of the audio and metadata which is being played out. And then Atema, the main encoding partner that are receiving the streams, the metadata, video and audio metadata streams, and performing the compression for distribution. Okay. So thinking ahead, okay, what happens now? We've got one broadcaster up and going. Of course, we are talking with lots of broadcasters about this. There's quite a lot of interest, so we hope that we'll get another one on board soon. This, by the way, this is not something that as Dolby we are pushing on trying to monetize. It's really more that this solves a problem for broadcasters and pay TV operators, and so we want to make sure that people know that this exists. That's the purpose of me talking today. Going forward, I'm going to be publishing a specification of exactly what the repository file is, probably with either the UHD Forum or maybe the SVTA, but in that, some kind of organization like that under their umbrella. And also some guidelines just to help implementers and so on. And then we expect products to evolve over time. And actually an interesting point just to kind of show where maybe things are going is Junger collaborated with SSL on providing a way that an SSL console can do monitoring of different audio presentations. So these could be different languages or different versions of the audio, but how that can be done with a console and with a mixer in real time. And so SSL and Junger have worked together in order to perform that integration. And we expect more of that kind of thing, like partners getting together to solve things and streamline workflows for their customers. And then we expect the formats to evolve. Like XAVC is actually kind of quite an old video. One great thing would be the adoption of JPEG XS, because actually that can be carried natively in a compressed form over 2110, so that would avoid the kind of decoding of the video during playout. The compressed video could just be played out over the network. So we're kind of expecting support of different video codecs, certainly going forward. Okay, that's all from me. Thank you very much.
Thank you.
Any questions?
We have time for just a couple questions if anybody has any. Or any questions for Andreas? Oh, hang on, let me get you the mic.
From Altra. Just interested to know if you use FPGAs for the audio compression or audio processing part.
Yes, thanks for the question. And the question was, if not everybody has heard it, he asked if the processing of audio is done on FPGAs. So in the younger audio devices, the processing itself is not done on FPGAs, it's done on a CPU, basically in the devices, yeah. Any more questions?
All right, 1, 2, 3, break.
do a shout out to Tina. She's managing all the things, but she's on the, she's not on the boat. So when we're back, shout out to Tina. So my name Willem van Most. I believe I've seen already a few faces which are here. And maybe first a question, who did hear about DMF or Dynamic Media Facility already? Okay, good. Then my slides are still needed. Good, thank you. So I quickly decided to go first because Vincent is going more in depth about the specific topic that you will see everywhere around the show. So it works when you enable this technology. So it's a little bit small, so I'll try to give you a quick introduction why EBU, the European Broadcasting Union, and the members are interested in all of this. It's a little bit like, I'll do a very shortcut to the story. I served in operations for 5 years as the operations manager at VRT. And one of the things I noticed is when you have pure IT guys coming into a gallery, for more the news gallery, you see those eyes going like this. Because you suddenly know, oh, story. No, we're not going to tell this story. He's not ready there yet. The satellite link is not done. So this needs to go first. The IT guys, they looked at us and they said, whoa, this is maybe where they invented agile. And these are media producers. These guys are very agile. But actually, if you look down the stack, and technology might not be as agile as what those guys need to have. Remember back in the days, moving from SD to HD, that meant ripping out all the cabling and putting new cabling in and start to build from scratch. At VRT, maybe we're not the fastest, but it took 1 year for a project to rebuild one full studio, and then the other one, the other one, the other one. So this is something that you probably won't like to do anymore, right? So another thing has happened as well. Our ecosystem completely changed. We had one cable up in the air or an antenna, and off we went to the public. Good. But now, of course, all of this has changed a little bit. I think, are the slides progressing? No. I need to click somewhere, but it doesn't. Yeah. Okay, thank you. So what we do see right now, all of the broadcasters companies, they need to be online. They need to have an online presence, right? But actually, if you look at it from a schematic point of view, this means we didn't do it before. Now we need to shift money and people into this distribution part. So small broadcaster, for instance, has around 100 people shifted suddenly into online website and creating all the experience you find like a Netflix or a Mediathek in Germany, or there are so many other examples. So this is a shift of money and budget. And all these things together means how can we produce more effective? Because we need to have more products in these shops. We have more shopping windows now. We have an online presence. We have our linear channels. So we need to produce more, and how can we be more efficient? So this was actually for EBU, the driver, to look into this. Sorry, if you can click again. Yeah. You may click. Yeah, I've been past this slide. So if we look back in the days, and this was when I started at the EBU, first time, there was the idea to move from SDI to IP. I thought, well, this is excellent. I thought all the work was done by changing from tapes to files. Suddenly we were in the realms of IT, but there's still one piece that we didn't fix yet, and that's our typical SDI cable. So you see a whole timeline, and I won't go into the details, but it took a while. From 2016, 2017, we had the standards, but actually if we move forward into time, need to click again, I'm afraid. Hey, it animates, wow. If we move to 2020, just after COVID, when I think most of us have done trials with software and how to be able to produce while you are not able to get into the same room or in the same studio with people. Even, I don't know if you know, but Belgium, we're cyclist mad guys. We have something like Tour de Flandre, and it needs to be there, even during COVID. So what did we do? We made sure that professional cyclists had phones at home, and we produced a virtual cyclist game of Tour de Flanders while having COVID. So we were really invested into making software work, and suddenly we realized but actually we can go much further into this, because we went to IP, but we didn't went to IT yet, because we have the same boxes as before, but with another connector at the back. So how can we be more flexible? And then we looked also a little bit at the technology. On the left-hand side, it's small for the back, but I'll just say it out loud. On the left-hand side, you find switch technology. So you buy an Ethernet switch. Back in the days when we started discussing 2110 versus where we are right now, there's a speed up of Ethernet switches of 64 times. Our workflows didn't grow as much. As a result, those switches are getting cheaper for the workflows we need to have, or we can run more workflows. On the right-hand side, you will see a graph about CPUs, because in CPU land you see actually a similar story. It's not that the frequency, the clock frequency of a CPU did boost up, but the amount of threads that you can run is just going crazy just in the last couple of months. So it was kind of flat, but now you see, last year I looked at it and it was 192 threads you could run, and now it's 384. So these numbers are just going wild. This is of course still the laws more, you know, the dices are getting smaller and you can do much more things. So when these things come together, you might think, well, why are we not moving whole our industry into off-the-shelf service? And then my dear friend Yevgen, who left the EBU but now works with AWS, came up with, hey Willem, do you know pets versus cattle? I said, no, what does this mean? Well, this is how the IT industry works. And this is how we are working. Like, he had two skin cats, those cats without any fur, and he had a snake. And of course, it's when you have pets at home and there's something wrong with the pet, you go to the vet, right? You take care of them, they have a diet, you nurture them back to health. But the big IT industry and all the cloud providers, if there's a server that broke down, you rip it out, you replace it by another one, and off you go. And it's the same if you produce milk. If the cow doesn't produce enough milk, you probably bring it to an asylum and you put a new cow in place to produce as much milk. And this is actually the flexibility and the force they have in the IT realm, and we don't have it. We do still support boxes. If I look at our support engineers, they work like this. Even with 2110, you look into your technical facility, boxes with another connector at the back. And from an operations point of view, I look at it and I see we spent engineering power up to the box. So this is the pets versus the cattle reality. So if we move into this side, even from a real broadcaster, you would save support, because there's only maybe 1 or 2 people that could support this, instead of per brand or per plate you see here a different person. So that, thank you. So that would be really great. So how does it look in real life? You would have a standard Ethernet network. You would run off-the-shelf servers on top with NICs, with GPUs, with DPUs, whatever you wish for. And we could run our applications just on top as if it was software. That's good. But there's another notion in the IT industry that they're using, and that's virtualization. But that's kind of heavy, so there's something new called Dockers, that you could you spin up a Docker and you kill a Docker. That's very flexible, right? So this is where we were looking at when we were discussing at the EBU, and we thought, well, this is just where we need to go. Suddenly, if you think about the media function, which could be a vision switcher or maybe an EQ, I don't know how granular you need to be, but imagine if you have a media function and you put this together as a graph. Suddenly, a graph of media functions or containers is a workflow, which is cool. And then you can script your workflow and spin up your workflow and bring it down again. So that's actually the whole idea. So we came together with a few people within the EBU. I'll skip this one because that's an obvious. That's an obvious one. So we came together with a few people at the EBU, and we thought, let's bring in the IT industry and let's bring in the virtualization industry and a few vendors. And we discussed this, and we came up with the idea like, oh, you have the media function, but lately the our industry has put a lot of effort in everything that, sorry to say so, doesn't create value. In the wings of a bow tie diagram, you see? So this is a media function. This changes your media. But we've discussed a lot about different metadata schemas, about different types of control. It's cool for engineering, but if you're somebody that cares about getting results and changing your media, this is actually what we should do, right? So we thought about different use cases. They're too small, but they're in a document, and you will get the document afterwards. So if you have all of this and you put them together as a graph, you have defined your workflow. You nod yes, and I think many people now start to see that this is really a way to go. Because next discussion could also be like, oh, if we apply this to a real broadcaster, this is a picture from CBC, it could look like a camera input, a video processor, a vision mixer, all of these connections in between. That's cool to have. And then maybe there's 2110 or IPMX to get all the flows into the cloud or your local cloud on-prem. And again, 2110 or SRT or WebRTC on the outside to get your flows out. Now, if we looked in practice, we see a lot of those connections up and running now, but they go outside of a compute, use 2110 and go back into the other compute. But if you use 2110, that's really cool, that's a great protocol, it's uncompressed, but each time you need to synchronize again, meaning you lose frames each time. And why would you go outside of a compute resource while your media functions are within the compute? So the next thought was, well, maybe we could just run all of these functions within memory. So I think it was last year, just before IBC, we popped out with a document called the Dynamic Media Facility Reference Architecture. And within this document, and you can download this, it's free to download and to read. Within the document, we describe actually a reference architecture, which is nothing more than a few layers. So the few layers, they will pop up on the right-hand side. There are 3 zones you should remember. There's the base layer here, and this is generic IT. As a broadcast industry, don't touch it. It's what the IT industry does. If we create servers again, it's a waste of time, it's a waste of money, right? There's a full industry that does this far bigger than we. So go for it. Infrastructure, networks, host platforms, and also container platforms. Don't create your own container platform again. Doesn't make sense. There's a layer on top of this, and that's what we call, well, that's more the media layer, in which we think you need to exchange media in the host or between the media functions. You need to have a media function that, of course, uses this. And then we decoupled also the application and the UI, whether it's a physical panel with buttons and knobs, or it's a touchscreen. Both can make sense. Both can make sense because for some productions you don't need to have 15 people in a gallery, right? You're probably better off with a small UI serving a very simple production and one person controlling a UI. This is not everything, because there are 3 cross-cutting concerns that we picked up from 2110 already as well. Of course, we need to provision those media functions, we need to orchestrate them, we need to control them, monitor them, and I've never seen a virus on SDI. Security through obscurity or secure direct ingest, whatever you want to call it. But on IP, we need to take care about security. Of course, this was something that was mentioned during the 2110 efforts, but it will pop even more now. There's something that will be applicable by the end of 2027, and that's the Cyber Resilience Act, meaning that every product which comes to market needs to be without any proven flaw in it. That's a big change coming ahead of us. So that's more or less the idea. So if we can use this type of framework, that would be really beneficial to the whole industry. Then we had a big meeting in November at EBU. We thought, who could be interested. So we invited just people that we thought, oh, maybe, I think, of course, Vincent, you were there with GV. We had Riedel, we had Lao, we had Matrox, we had Google, AWS, Intel, NVIDIA, a huge bunch of people. And we just explained this. And I think within 5 minutes, we agreed that this media exchange layer was probably the thing to do first. And even better, there were 2 companies that stood up and said, oh, and we want to contribute code to this project. So that's really good. That's November last year. Last year? Yeah, last year. Need to think about the years. That's November last year, and then we said, how can we do a setup? Because, well, that sounds very European, and maybe Americans will think, oh no, it's not invented here, so it's a small European thing. So we asked CBC, and CBC proposed to do the same meeting in Montreal, and to join together with the NABA, the North American Broadcast Association. And then we discussed even further, and we said, well, we're not code developers. We've done this before, and we know we're not perfect into this. So we got out and searched for help at the Linux Foundation. They know how to handle open source code. They've done this before in many, many other projects. So we linked together with these guys, and this is how we kicked off actually the project. First of all, we started with a Tiger team, a small team, just to come up with a proposal. You know, when there's no proposal on the table, you can discuss for ages. But now we thought, let's start with the Tiger team, come up with a proposal, and then just throw rocks at it. This is what happened. And this is also what you see right now. So we booted the project officially in June. In June, we said there's a requirements council, there's a technical steering committee, and there are a lot of other partners just joining in on the calls, trying to help out. This is what started in June. Then there's the holiday season, July and August, and this is September, and you see a lot of applications already on the show. So I try to keep it very high level, just saying there's a big overview. There's something called dynamic media facility with ideas of provisioning, orchestration, control, monitoring, all these different layers. But for now, what's really important to this IBC show is this media exchange layer. And we're going to do nothing if it's not specific to media. So if it's the IT industry, we will reuse whatever is out there, but I'm not stealing the thunder from Vincent.
Thank you.
So Vincent, with this being said, I think it's introduction enough. And then I would say I hand it over to you. Unless there's any questions meanwhile, by the way.
Some questions maybe? You want to keep that? Hello everyone, thank you Willem for warming up the crowd. Fantastic first act. I'm Vincent Troussard, VP Software Architecture at Grass Valley and Chairman of the Technical Steering Committee for the EBU DMF MXL initiative. This will slightly overlap with what you've described, but I'll take a different angle. So over the last 20 years, 25 years in live production, we went from fixed function dedicated hardware solutions to completely dematerialized software-defined media functions that can execute on-prem, in container environment, or in virtual machines, or in the cloud, or even using accelerators in the cloud. The compute power, as you mentioned, is extremely is orders of magnitude what it used to be 20 years ago. I used to work on one of the first play-out solution. One HD channel per full server. That's the most we could do with one box. Now we can do dozens of channels on a fat server. So it is massively more powerful. We have fast GPUs, fast network infrastructures. So we see that we have more available to us and more flexible execution environments as well. So if we focus on the second half of this, on the first half of the graph, what enabled this transition from fixed function to virtualized software is going from SDI to IP, for example, SMPTE 2110. Something that was great with 2110 is that it was kind of similar to SDI. Line alignment, pixel alignment, predictable timing. So all the attributes of 2110 of SDI were mostly preserved. It's the same mindset. So it's synchronous, it's real time, it's clocked, which was comfortable for people who were used to SDI. Sorry, I lost one. However, if we look at the second half of the graph where we go to purely software environments, these core attributes of SDI, synchronicity, real-time, suddenly become a hindrance. If you want to execute multiple media functions back-to-back, you don't want to wait for the end of the frame to be transmitted to work on your next step, and you keep adding latencies. We also, for example, since COVID, everybody was cobbling together something based on NDI, CDI, SRT RIST, even within the same container environment, within the same server, looping in, looping out, again adding latency. So there's something better that we need to implement. At Grass Valley, we've been building AMP for 7 years now. We've been using shared memory models, and this is something that we want to contribute and work with the DMF initiative to have a shared memory model. So Willem presented the layered approach for EBU DMF. MXL is focusing exclusively on the media exchange. This means that we're not covering provisioning on purpose. We're not covering flow discovery, flow registration. All of this is not part of DMF. So by itself, the DMF is incomplete. It will need upper layers to help you find, discover, register flows, but it's a fundamental layer that will enable us to build on top of. So yeah, exclusively focusing on MXL. Another analogy that we use at Grass Valley is MXL defines the plumbing, the utilities between multiple houses. Multiple vendors have their own platforms, software-defined platforms. They all have different platforms now. But we need a way to communicate. We need to be able to exchange the best-of-breed audio processing technology with the best-of-breed video processing technology. And customers want to have this flexibility. At the moment, it's very difficult to pick and choose software-defined media functions from multiple vendors in a single house or in the house that you get to choose. And this is what MXL will allow you to achieve. Quick timeline, as Willem said, last year, September, first discussion. In 2024, exactly today, exactly that specific day, the day before the end of IBC, I met with CBC guys, with EBU, and the idea was circulated, well, we should do something. So it's exactly 365 days today from this first day. And in this industry, we're not really great at moving fast, but within a year, we have pictures and interrupt, which I think is quite amazing. So it moved very, very, very rapidly. I won't go in details here, but the Geneva Convention in November 2024. Multiple vendors, Tiger team. So yes, the Tiger team was formed, and as you said, rocks were thrown at us. But yeah, that's part of the design, the initial kickoff. But it was essential to bootstrap the initiative. By NAB this year, so there's a typo here, 2025. By NAB, we had our first internal demos. Pictures were moving, no sound, just video. It was about to get real, and it already raised quite a lot of interest from multiple vendors and customers. And people ask us, where's the code? It's supposed to be open source, but where's the code? Well, we could not release the code to a wider audience without a proper charter, a proper open source project. And this is what the Linux Foundation gave us, as you mentioned. It's a charter, it's rules of the road. So who's contributing what under which license? If there is a conflict I want to do that, and you want to do that. How do we resolve this conflict? So it actually took quite a while to get the charter in place, but once we had the charter in place, all the code was made available on GitHub. Everything is Apache v2 license, so no strings attached, but you need to release your code under the Apache v2 license as well. Everything is available on GitHub. Multiple vendors already active, showing demonstrations, showing live code, live demos, and interop already between vendors this year. So, this is time to roll up our sleeves because it will be quite technical. So, hopefully this is what you came for. So after this Geneva meeting, we identified the key requirements. First one, we need to cover intra-host sharing, so I have multiple containers running on a big system. How do I exchange memory buffers? So that's what we call intra-host memory sharing. But it needs to also cover inter-host media sharing. So if I'm in a big data center, I have racks and racks of servers. They are usually connected using a very, very fast network environment, what we call a fabric. So on this fabric, this is nothing new for the IT technology. For broadcast world, this is something a bit new, or that's something that we never used. But RDMA, elastic fabric adapter, all of these technologies can accelerate media movement from one host to another without involving the software, without involving the operating system. So it's wire speed, as fast as it goes, as it can, it will saturate the link. So this is something that we should leverage. The IT industry, the AI industry is investing billions of dollars on this technology in all data centers. We should be using that. We should not try to invent something else and dispatch small packets every 7 microseconds, which is horrible. PCs are horrible at dealing with small packets, evenly spaced in time. PCs and servers are good at big buffers and bulk transfers. And this is what technologies such as libfabric, RDMA, and so on will provide us. And we're just building on top of the shoulders of giants. We're leveraging what the IT industry is doing and not building against it. We want optimal performance. For example, what I said about packetization across containers and then encoding SRT, this is a waste of resource. We're wasting a codec, we're wasting a decoder. Packetizing is expensive. Why are we doing that? The buffer is on the same machine. Share the buffer instead. So it's orders and orders of magnitude more efficient to just share a pointer or share a buffer than to encode and ship. So we're not doing that. So it needs to scale to thousands of flows, not just 10 flows, thousands, tens of thousands of flows on a single machine. And we want I wrote low latency. It's actually ultra low latency. If you have a line of a picture, if you have a couple samples, you can start consuming them as fast as possible. So we saw some graphs from one vendor comparing 2110 latency to be about 33 milliseconds for 1080i 59. RDMA was about 1 millisecond to move the full frame across the wire, and with the MXL it was 0. It's just instant, it's there. So fantastic latency, suitable for video use case and audio use cases. It's interesting, in the list of logos that you saw, you had video-centric vendors and audio-centric vendors, and their requirements are not quite the same. So the audio guys will want, I want every sample one by one, and the other guys, we'll give you a frame, and that's it. So we have to accommodate the two use cases. Again, let's not reinvent what we don't need to reinvent. JTNM, flows and grains model, it's well defined, well explained, well documented, so let's build on top of that. And the NMOS JSON definition for the flows, it exists. It defines the width, the height, the bit packing, the resolution, and all that. Let's not invent yet another horrible way to describe video. There are many ways. Let's use what has been standardized. So we're leveraging what exists now, and we're leveraging terminology that we know. So for the broadcast industry, it won't be new. This is something that we know. This is a revolution. We're not working on a specification. We're not working on a document. We're working on an SDK. The measure of success of this project will be the delivery of version 1.0 of the production quality SDK that works across vendor, not a document. We've seen this with SRT versus RIST. SRT SDK first, and we'll standardize it afterwards. Everybody got the SDK, and it just worked. And then RIST, write the spec, and then lots of different implementation that may not be compatible. So that's a good example why the SDK first is something that promotes interop, and that's what we're seeing today. After a year of development, we have interop. Small library. We want this to work on Raspberry Pis, embedded audio devices, to hyperscaler in the cloud. So must not bring Kubernetes with it. It must work with containers, it must work with Kubernetes, with cloud hyperscalers, but also small Raspberry Pis and small devices. We want this to be very scalable and work in multiple execution environments. Basically, it's no strings attached. We're not forcing the broadcast vendor to actually bring a full stack of software to get to MXL. It's a small library. As you said, security is super important, so we need to make sure that if I have two productions running on my server, vendor A or customer A cannot see the flows of customer B, so we have to protect, isolate, segregate the different flows. We also want to have a model where we can move and describe video buffers and audio buffers where it lives. So my buffer came on my GPU. I would like to leave it on the GPU until I need it on my host. My buffer is on my GPU. I need to send it to another GPU on another machine. I'd like to migrate the buffer to the other GPU without involving the CPU. So again, using fabric technologies to move the buffers elsewhere. Using acceleration if possible. Okay, I covered that. So how does it work? This is when we roll up our sleeves. Simple C API, C++20 implementation, modern code under the hood. The shim at the top is plain C for ABI binary compatibility over time. It's basically the flows and grains model. A flow has a unique ID like in NMOS. The flow for video and ancillary data, it's grains living in shared memory in memory. And each video frame lives in one grain. Simple. For audio, we didn't want to shoehorn the concept of audio into a video grain or something that is too big. So we have another ring buffer type. I think I covered that a bit later. Another ring buffer type, I'll cover that a bit later. So we want to memory map the buffers. So as a consumer, you just do an mmap of the memory region, and you have direct access to the buffer. You don't need to ask for the buffer to be sent or given to you. You read the buffer. We don't use the terminology senders and receivers. We use readers and writers. You read in place, you write in place. So again, more efficient. How does it work under the hood? By limiting ourselves to Linux or Unix-like environments, so no Windows support, by limiting to Linux environments or style, macOS works as well, we're using RAM virtual drives, RAM drives, TempFS, to host a region of shared memory. Why TempFS? Well, we need to find a way to share memory across containers in a secure manner. I don't want to give IPC access to all my containers running on AWS or running on my host. I want my IPC, my interprocess objects to be closed and secure within the container, but I want to put something in my container and make something available. In containers, you can actually map and mount a volume, a virtual disk. It's still just pages in RAM. It's not adding any very minimal overhead. But you can treat it as a virtual volume that you give to a container and you mount when you spin up your container, and then you can actually see the flows. Since it really just looks like a file on disk, you memory map that region, and you have access to the memory buffer. We want this to be super secure. So this is geek mode on, sorry, I just turned on the geek mode. We cannot even use a mutex or semaphore to access the memory region because you need write access in the memory region. We don't want to give write access to readers. So we're using a mutex under the hood so to detect when something has changed in the memory counter, and then the reader knows that something has changed without having to lock a mutex in that memory region. Geek mode off. So that's the end of the geeking out, but basically we want this to be super secure. Since it's a virtual file system, you get all the benefits of the Unix permission schemes as well. So I want my group called morning production and my group called nighttime newscast. And you get groups and user and permission masks and bit masks to allow access or block access to some flows and give access to others. Since it's a virtual file system, you can even group your flows into virtual folders. We call them MXL domain. So I have my morning show, it's a domain where the flows live. I can have on the same machine, using the same compute, a second domain, a second volume that is actually customer X doing a game of soccer or whatnot. And then you partition your flows into different virtual paths. And then you map these domains into the containers, so the containers only sees what it needs to see. Again, very secure. It's very slow. Okay, multiple types of ring buffer. I don't know how much time I have left. So the first one is the granular ring buffer for grains, like video, something that is fixed size. A video frame, something like a VANC packet, which has an upper boundary in 2110. So VANC and video, they go in a granular ring buffer. So ring buffer, each slot index in the ring buffer is a different frame or grain. The time of the ring buffer is basically, you start with PTP time, the epoch. You divide by, you do a modulo of the duration of your grain, so 33 milliseconds or 20 milliseconds, and the remainder is the index where you should be. So it's basically continuously increasing index in a ring buffer. You know where the head is, the head keeps moving, and the readers can choose to read wherever they want in the ring buffer, which gives you lots of power. If you have cameras, for example, sending video from across the world, and you have another camera that's local, and if they carry their own timestamp, you can actually hide the latency, because they actually can write at the right place in the ring buffer, and you can choose to roll back time and consume your flows synchronously between the two cameras. So one will have more data in the future, but you just read a little back, and then you can realign perfectly the two flows, because you have enough history in your ring buffer. The history, the size of the ring buffer is configurable per domain, so there's an option file where you can increase and make the history bigger depending on your use case. Again, here, so the grain rate is the frame rate, so that's super simple. It's super low latency because when you read a grain, so the API is MXL get data or get grain, I can't remember what the API is. You get the data with a timeout. If you get something, you have to look in the header. You know what? This is a grain. It has 20 valid bytes out of 5 megabytes. So someone wrote a bit of data in it, and it is incomplete. So the reader must verify if the data is complete, allowing writers to write line by line if they choose to do so. So if you have a JPEG access decoder that can decode a couple lines, you can actually write them as you go and be very low latency. So that's what we call slices or partial grain. It doesn't really need to be a slice. It's not 8 versus 4 versus 16. It's some data is written, and you have to verify if it is complete. I said multiple readers, but you can also have multiple writers in the same ring buffer. So if you have redundant flows, and if you can guarantee that you have -7-like reception, so the perfectly identical data coming on two paths, could actually have collaboration between two writers. So if one goes down, the other one carries on, and you have redundancy at flow writing time, and multiple readers, not just two, as many as you want, readers that can choose to read now or slightly in the past, and so on. For video, we chose to limit as much as possible the video formats that we want to support to promote interrupt, and that's the reason why we had interrupt. So the Zoom guys will want RGB 445, RGB 888, and some guys will want planar 16. And we had to choose. We had to choose something that is suitable for most use cases. Broadcast is still 10-bit YUV 422. So the V210 format, packed format, lets you carry 10-bit YUV 422. SDR or HDR, so it was good enough for 99% of what broadcast is, so we settled with that. Ancillary data, It's the RFC 8331, which is the RFC used by 2110-40. So it's exactly the same without the RTP header at the top. How much time do I have?
It's good.
Okay. So I said it's a virtual file system. So this is what it looks like. So look at the recording if you cannot see what's written. But basically, this is the flow ID. .mxl flow, that's a folder, that's a directory, and within that folder you have the data header, the grains subfolder. So this is the header where you have the few text that will tell you something has changed, so you'll link the data object. Then the grain subfolder has as many grains as it needs for the history duration that you chose in your options files. 5 HD pictures of type V210. And as a reader, the SDK will let you memory map these regions and consume the buffers without any single mem copy. The .json here is really just the NMOS JSON flow definition as found through the standard schemas in NMOS ISO 4. Any questions about that?
Yeah, you're about one.
Okay. Audio, one big buffer, and then you have first channel, second channel, third channel, so it's multi-channel audio, if you choose to have multi-channel audio. All the samples are ordered per channel, making it easy for you to derive a pointer and just iterate over the samples. You don't have to demux or anything like that. Structured slightly differently. I won't go into that. Important, we're leveraging libfabric to move grains and move buffers around from sources to destination. This is something that is still being worked on, not available at the moment, will be available as part of version 1.0. So roadmap to version 1.0. We need to add audio-video synchronization objects. So it's easy to consume audio, it's easy to consume video, but if you want to consume from both ring buffers, how do you synchronize everything? So we'll add that. Fabrics API, as I said, a Rust API and GStreamer native plugins written in Rust that will let you do full I/O using GStreamer. You need to define a qualification and validation process. We want, when 1.0 is released, we want broadcasters to be confident this is compatible, it will work with everywhere. So we want some kind of approval or qualification process, documentation, bug fixes. Post 1.1, another type of ring buffer that will allow us to carry data that is timed, not periodic, and random size. So it doesn't fit in any ring buffer, but if you think about 2110-41 or fast metadata, FMX, we need to be able to carry something like that, to carry audio metadata and so on. So this is coming soon because we know we need that. What's next? It's going to be defined by the requirements console. So we're not inventing stuff, it needs to go through the requirements console, and then the technical steering committee will start implementing the features. 30 seconds for questions.
How are we going to do timestamps?
Okay, that's a very good question. I went very rapidly on that. At the moment, everything is based on origin timestamps. So the origin timestamp is used to derive the position in the ring buffer. So everything is actually based on origin timestamp. The grain carries its own timestamp as well. We're thinking that maybe we need to enrich the model with potentially additional timestamps, but at the moment everything is OTS based, so origin capture timestamp, not arrival timestamp. So if you have the origin timestamp, you carry it. If you don't have it, then you restamp it at entry time. But everything, all the maths is based on...
Carried how?
Well, internally, it's sharing. If you have, for example, a stream that comes from 2110, you may actually want to use the RTP header timestamp and unroll it to a PTP epoch time. So different protocols may actually carry their own origin timestamp. In AMP, we have a mechanism to carry OTS as well. So if you have a mechanism to carry the origin timestamp, do it, please. It will make your maths much easier. If you don't have it, if you're using a protocol that doesn't have OTSs, then you have to derive them from the arrival timestamp. But the mechanism to transport the timestamp is not defined at the edge of MXL. Internally, we carry everything, but it needs the external protocol needs to support it. Fantastic question, thank you.
One question I think maybe some of you will want to ask is, how can they contribute?
I think it's on my next slide. Well,
But basically, it's on GitHub, DMF-MXL, DMF-MXL project on GitHub. All the source code is available. Contribution and welcome. If you want to join the mailing list, if you go on the GitHub page, contributing.md, there's a mailing list. Send an email. We're going to send you the Slack channels. There's active conversations going on. Source code, pull requests, source code, and all of that. So join us. The more, the merrier. Thank you. Any other questions?
Well, two parts. Is there going to be any method of offsetting the timestamp? For instance, an RF camera, where you know the latency is 2 frames or 4 frames. Will you be able to program that so that it maintains the origin timestamp? And the second part was
We
what?
don't have time. You need to go fast.
I will answer the question outside.
Okay.
Yeah. All right. Thank you, everybody. We have the next set of people coming on board, so thank you very much.
Kathy's in witness protection. I'm going to have a, is this limey water, and that's the clicker. So I just have to put the very tempting donuts on your table here, and some chocolate brownies and more donuts. Those sunglasses or something.
Oh, mine?
Yes.
Are they bad?
No, they're fine.
Oh.
They're a look. It's like
It's nice. We're gonna come out of here and I'm gonna be like.
No. I have a pair of very hip sunglasses, but they're at home in my car because I never thought it would be sunny in Amsterdam. And largely it's usually not, but.
But when it is, it's like, oh, my eyes are very sensitive. You don't like flavored water?
It's limes, it's okay.
I love limes. I love key lime pie. That's one of my favorites. So we went to Miami and Ray is a fan of key lime pie. Every single restaurant, every single bakery we went to, nope, we're out of key lime pie.
Yeah, that'll happen.
Well, when I didn't speak quite that loud.
Great. Thank you very much. So we'll see how you feel after. So I'm John Myatt. As Tina mentioned, this. Whoa, that's.
We'll be turned around here
Okay,
in a second.
yeah, that's having trouble staying still. So as Tina mentioned, this is the Ames, AMWA, VSF, did I leave anybody out, IP showcase. And so first we'll have acronym puzzle. What is Ames? Ames is the Alliance for IP Media Solutions, an organization that was formed to solve a problem about 10 years ago now, where there were a bunch of competing standards of how we would do IP in, sort of baseband networks. And at the time, there were a bunch of competing proposals, and Ames was a mechanism to get the industry onto a common technical roadmap. Very successful. As we now are talking down the, EBU, DMF, MXL kind of story arc, it's a similar situation, and I think that EBU has done a good job of showing leadership on how to get the industry again onto a common technical roadmap. And I hope that the DMF project serves that purpose in some of the things that we're talking about here today. The Video Services Forum is VSF, and AMWA, the Advanced Media Workflow Association. So you just get some words, and I have the privilege of being a director of both the AMWA and the VSF. But today I'm talking a little bit about history. So you might one day in your life have worked with analog television. And analog television, you know, I never worked on analog, but I know people who did. And in the video world, wow, here's an example of how to not upscale video. In the video world, 270 megabit video on serial digital in 1990 was a fantastic accomplishment. We were all very proud as an industry that we had 270 megabit digital SDI because our friends in IT had 10 megabit Ethernet. So we had 270 megabits, they had 10 megabits, we were winning. And then, of course, they had 100 megabits, but we still had 270, so that was fine. Then they had gigabit Ethernet. But that's okay, we had 1.5. So television wins. And then, of course, we had 3 gigabit, but then they had 10. So, now we're losing. And of course, then they have 100. Now they have 400. So, and they have 800 and 1600 now too, if you wish. So, it's a really two very different industries. Now, why? Why can the IT industry do this? And as a television industry, we do that. Well, it's about economics. And so the question is, you know, will IP for video replace coaxial cable? Well, if you asked that question 10 years ago, you'd get in a fight and you'd get an argument, right? I remember a well-known engineer who's now a director of engineering at a large broadcaster years ago saying, we will never ever do this because those IT products can't do something, you know, something. He's now the proud owner of a very large SMPTE 2110 network. Because ultimately these technologies prove themselves. They do work. Every transaction of your bank goes through IP. Surely if it's good enough for money, it's good enough for television, because television is money. Well, all of this is driven by economics. So this chart, which is hard to read, but it'll be posted online later, this is the dollars per gigabit per port for IP switches. And so this top line, 25 roughly dollars per gigabit per port, and isn't really going down very fast anymore, is for gigabit Ethernet for 1 gig. Now, why is that curve so flat? Well, because it used to be back here, you know, this is only back to 2017. If this chart went back 20 years, you'd see a huge decline in that price, but it's out on its asymptote. It's out in its very flat part. This one is 10 gigabit Ethernet. Again, came down, kind of flattened out. It's, you know, around $10 a port per gigabit per port. These lines down here are 25 and 100 gigabit, which really track about the same. Why? Because that's what's current. So they came down from, you know, sort of $6 to $3 per gigabit per port. 400 gigabit Ethernet, when it launched, was already well below. It was below $1 per gigabit per port in broad market switches. That's interesting data, right? You say if really what we're moving is gigabits, the fact that we're on these, you know, 100 gig and 400 gig kind of port speeds, that's really the cost of the fabric. If you asked what's the price per port for SDI, just for the chipsets alone, just the chips, just the Genome chips to do SDI are still up in the $10 to $15 per port range, even if you buy a lot of them. And how many vendors in the world make transceivers for SDI? It's a shockingly low number. It's like 2. There's Semtech and there's somebody else. And there's one in China that I don't know who they are. So really, the whole thing is about 3 different economies, right? So the television broadcast equipment business, you know, Imagine, Grass Valley, Evertz, Riedel, Lavo, all of us, right? If you put all of us together, we think, oh, this is a pretty big economy, all these vendors, right? But we're tiny. Television is a very small industry compared to telecom. Why do we have all these lasers, 100 gigabit lasers and 50 gigabit lasers and receivers and all this? We don't have them because the television industry needed them. We have them because the telecom industry needed them. They're just tweaked up parts from doing Sonnet, doing SDH, doing all the different IP networks. Well, the telecom industry, they used to think they were big because they had all their own special equipment, but really telecom's not so big either. The big industry is the IT world. If you took the R&D budgets of every broadcast manufacturer, maybe even including Sony, and put them all together, it's still smaller than Cisco. It's still smaller than Arista. It's still smaller than Juniper, probably. And if you put the IT industry together, oh, it's much smaller, right? So it's the economics of this huge industry that drives the innovation that makes all the other things affordable. So as a television industry, we have to pay attention to what they're doing because that's ultimately what's going to provide the best cost per gigabit per port, cost per core gigahertz core of processing, cost per memory utilization, you name it. That's what's driving the economics that we live in. If only they would need camera lenses. That would really help, but no. So how's this play in practice? Well, if you have a Yamaha audio console, I don't want to pick on Yamaha, I'm sorry if anyone hears from Yamaha. If you had a Yamaha audio console and you wanted to get some audio from your video into it, like over SDI, you can buy an SDI card for that console, and it's about $4,000. If you wanted to get some SDI into your PC, it's $1,000 or so. If you wanted to get 10 gigabit Ethernet into your PC, it's $250. By the way, those are 10-year ago prices. That's 10 years ago those things cost so little. What is it now? Well, now, if you want a card for your PC, it's like $500. It's twice as many ports, and probably they're 12 gig ports. If you want to get IP into your PC, it's 25 gig instead of 10 gig now, but same price. And you could probably find that less expensive. You want that SDI special board for your audio console? It's about the same price it ever was. Why? Why does all this happen? Well, because for us as an industry, this transition from SDI to IP is part 2 of a story. The story started 20, 30 years ago when we started putting processes in software. And people don't realize that how long this has been happening. 30 years ago, we introduced a video server that was, SDI went in and out, but it was a computer, and it had codecs and did it mostly in software. 30 years ago. And that wasn't just us. Tech had one, other people had one around the same time. But this movement of doing the processing in software started that long ago and has really continued all through this time. We've been moving more and more functionality of the television infrastructure into software. So now, finally, now that we have Ethernet that's good enough, we put the pixels on IP. Again, not shocking. 10 years ago, you could get an argument. Now, people do it. Everybody does it. What's the third step? What's next? Well, what's next is really the systemization. How do we do things on demand? How do we use the fact that the signals are on IP, the processes are in software, to have dynamic media workflows, to spin things up, so to speak? That's the next big thing. All right, so now I'm ahead of myself. So ultimately, these IP architectures work. The IT industry has provided some nice tools for observability, for knowing what's happening and how it's happening. But the next step really is up to us and our applications. How do you deploy things? What are the tools for doing that? How do you, in fact, turn doing all these things deployably in IP from an engineering exercise into an operational exercise? And that's what we have as their next transition as an industry. So MXL is an important step in that, in terms of being like the plumbing. But the layers above that are what I'm here to talk about today. So that was the world's longest introduction to a talk about deployment. Deployment tools, it's an interesting world, right? Because a lot of what we're going to next in television is loosely called infrastructure as code. You literally have text files, more or less, that describe what am I doing? What is the target state of the system? What is, you want to deploy 5 playout chains. There's a text file that says chain 1 is doing this, it's connected here, da-da-da-da-da. And ideally, you have that and you change control it and you put it in GitHub or someplace to keep it very, very safe because it describes your plant. And if you make a small change, you then re-execute that file and whatever tool it is makes that change in your plant. And that all sounds great. But what does that mean? Well, ideally, you can make small controlled changes, you execute the file, that magic little tweak happens, and everything is exactly as you wish. So we're going to talk about some tools that the IT industry uses and we use now in television to do this. So one is called Ansible. You might have heard of Ansible. One is called Terraform. So Ansible's logo looks like that. Terraform I had to look up, but that's their logo. And the third one is Kubernetes. It took me a long time to learn to say that. Kubernetes. No, that's not a word in any language that I know of. And then, is it?
Greek.
Oh, in Greek it is a word. Okay. I learned.
Down there is Kubernetes. Fiber.
Okay. Ah. I learn new each day.
It all is Greek to me.
Apropos. And then the fourth term, CI/CD. Who can tell me, other than you, you probably know, what is CI/CD? Yes. So as a software vendor, we do this, right? We, every night, my team, they make changes in the code, they put in their, they commit their changes. That's the word, you commit your changes. And then somebody runs, kicks off the build. They merge everybody's changes and they hit go, and then Jenkins is a common tool, goes and makes the build and loads up the test automation and runs a whole bunch of tests overnight, and the next morning we decide if we want to accept everybody's changes from yesterday. It's a great system, and that's what we mean by continuous integration, continuous development is literally that process of making small incremental changes and making tests to make sure that you've successfully implemented those things. And then you freeze for 6 weeks while you run the Olympics. But the last thing I'm going to mention is single source of truth, and you'll hear this expression as well, a single source of truth. And this is an idea that you have a common repository of facts that other systems in your plant can rely on. So first we'll talk about Ansible. So Ansible, in a funny way, Ansible is an automation tool, but it also can automate provisioning things. So Ansible literally is like a scripting engine that follows your instructions. And in Ansible, like we say, you build and change and revise your infrastructure by defining it in a file, or a set of text files, really. Nobody makes one giant Ansible script unless they're like a crazy person. And of course, in the Ansible lingo, Ansible has things called playbooks. So if you buy like a switch from Arista, they have a collection, is their word, of Ansible playbooks that know how to configure DHCP, configure a port helper, whatever. And then in your script, you can say, okay, for all my switches, do this, for that switch, do that, where the mechanics are in those playbooks. And that's great, except, it's not as great as it could be. So, do you need to write all these playbooks? Well, no, because most of the vendors do have some playbooks, but there's not playbooks for common video things. So, like, we have a customer in Germany who would like us to supply a playbook for SNP. And so I said, okay, what objectives would you like that playbook to do? Because in Ansible, you have each play in the playbook is an objective that says, configure a frame sync or do this or do that. And so that's the discussion we're in now, is what are the objectives? but there's not a common agreement in the industry on what are the right objectives, so it makes it a little difficult to write a playbook. But we all get there. So then there's Terraform. So remember we said Ansible is an automation tool that does provisioning. Terraform is the other way around. It's a provisioning tool that also does some automation, because that's how life works. Again, you build and change and revise your infrastructure by putting it all in a file. Terraform's language is that they have providers, where a provider is a plugin that provides the instructions, and resources are the things that those instructions operate on. So when you use, say, Terraform to deploy something, that's what it does, is it uses the providers and does all those things. Now, this language and this structure that they use is about achieving something called idempotency. And we'll talk about that word because it's a scary word. It's a scary term, but it's also super important, idempotency. So the idea of idempotency is exactly that when you apply the file, or when you execute the file, it only changes what you changed. That's the objective of all these tools, is that if you make a small change, it only does the thing you had. Well, to achieve that requires a lot of very careful work, because say you have a script that spins up a bunch of virtual machines, and you make a little change to it and you run it again. It would be bad if it spun up again all those same machines that were already running, so now you have two. So you have to be very careful in the construction of these things to understand the resources and the current footprint. But that's what idempotency is about, is achieving that result. There are a pretty good collection of third-party things for Terraform as well. Now, Kubernetes is a cluster orchestrator that does also some provisioning and some automation. So these things are all a little bit duplicative of each other, but they all exist and they all get used. So if you're using a big Kubernetes cluster, chances are you're using the Kubernetes language to manage that cluster. And again, you build and change and revise based on a file. All these files are in each one their own language, of course. And in Kubernetes, you have objects, which are application objects or policy objects or instances. Objects have a desired state. The file describes the desired state. And then the Kubernetes cluster orchestrator does whatever it has to do to achieve that state. So if the state is that you should have 3, playout systems or 2 playout systems, and then there's only one, the orchestrator will pop up and say, oh, I need to make another. So that's kind of the driver of redundancy in the Kubernetes world. And again, its main focus is about how do you map applications into a cluster. So one of the concepts of the DMF, I don't know if it's going to be the forever concept, but one of the early concepts is that it's targeting a Kubernetes kind of environment. And if you go to Amazon, one of the things you can order is an elastic Kubernetes cluster that becomes as big or small as you need it, and you deploy your objects into that cluster, and you deploy more objects into that cluster, and it just keeps growing or shrinking to do whatever it is you're doing. It's a really fantastic thing. You can also build one on-prem by, using other software, but it's a common object. And honestly, you can also buy such a cluster from Google and probably other cloud providers as well. And they're all similar enough that you can make things work. So Kubernetes is a very extensible thing. So this is all well and good, but we glossed through 2 words in there. So the first word that we talked about was immutable. Now, what does immutable mean? Well, it means that you can't change it, or it doesn't change. Now, we usually use this for the concept of identity. So that's interesting when you talk about virtual resources, because if I spin up a playout channel, and then I use that same template to spin up another one, are they the same or are they different? And how does the rest of the system refer to them? Because names are important, So that's the immutability challenge, is that identifiers need to be immutable. So if I spin up something with an identity, that's a thing, right? If I spin it up with another identity, it's a copy of the thing, it's a different one. If I spin it up with the same identity, then all these tools say, that's the same one over again, so make sure there's only one. And then idempotency is the other word where it's about when I implement the change or when I implement the file over again, that it only makes the change I changed, and it doesn't also have some side effect of making more resources or accidentally destroying resources that I cared about. So CI/CD we sort of talked about. It's this process of make changes, test them, but do it over and over again in small cycles and really testing the result each time. So it's what we do in the software world when we develop applications, but it's also something that as we do software-based applications for production and playout and distribution, we need to employ a similar methodology. You try it in your sandbox, and if it's all working perfectly, then you deploy it to production. And those are the words we use in websites and other things, is deploy to test, deploy to production. And it's these same kinds of tools are used for that we're using for software going forward. And lastly, there's single source of truth. So there are a lot of bits and pieces of information in these IT systems that you need to keep track of, and you'd like there to be one repository of them. So there are some common ones. Netbox is one, Infoblox is one, there's about 20 others. In some places like in Amazon, there's probably some special ones that are well known in Amazon. Each thing in your network has a truth. This water glass, if it had a serial number, it would have an identity. But what Netbox and these other systems are good at is being repositories of truth. So they're not really a source of truth, but they're often a source of desired state. So when we talk about these systems that are deploying and modifying software based on achieving a consistent state, people use Netbox and Infoblox and other things to store that state and to refer to it and to pull back and say, okay, what is the desired outcome of the system? But you really have to think about, is Netbox a source of truth or is it a holder of what you told it? And often people think it's a source of truth, but it's really a holder of what you told it. Might be true, might not. And that's where you have to kind of keep careful. So IPAM, IP address management, is a thing that you'll hear about over and over again. And often Netbox is a part of an overall IPAM system, where at least it's the source of intention. It's the source of what you want things to be. And then, how do you manage your IP addresses? Well, you could use DHCP. Many people do. And you can actually even automate that DHCP also updates Netbox to reflect what it allocated. You can do that. I've never really seen people do it, but you could do it. DNS, the same thing. You can have your DHCP server update DNS to say what it did, and many people do that. That's like critical. And then there's some other tools. All to say, all of these other tools, Ansible, Terraform, Kubernetes, they all expect to interact with DNS. And ultimately, DNS becomes a critical resource in all of these systems because everything you do that's dynamically addressed or dynamically named expects to find and interact with all those parts in DNS, in the domain name system. And then, of course, they can either push or pull from Netbox if you want a human interface. So I leave you with what I call the meta question, which is, why do we care about any of this? Well, we care about this because in the old days, if you were a television engineer in the analog days, no one expected you to design the camera, but everybody had a green screwdriver and knew how to use it. Well, most people did anyway. So you did have to understand enough to understand how to adjust the camera. And that involved a lot of understanding of how it worked. But if you think about a complex television facility today, you've got file-based workflows. If something happened where your MAM and your traffic and automation system weren't like sending the files to the right places, how many people in your plant could debug that? Hopefully at least one, right? Because you get in a bad state pretty quick if the automation isn't triggering the file workflow to get the right files to the right places. And that's why we expect people in the plant to understand how does that stuff work. Well, once we go to dynamic media facilities and dynamic deployment, we're going to expect that to effectively own and manage an operation that uses that technology also is going to require people to understand, at least at a basic level, how it works and have at least a basic operations and maintenance ability to keep it working. And that's hard, but it's kind of like the other part of, 10 years ago we all said 2110 was hard and television engineers were going to have to learn about IP, and they have. And now we say, well, to do dynamic media facilities, television engineers are going to have to know about deployment tools and that stuff, and they will. But it's work, and we all go through it together. And I leave you with that.
Thank you, John.
Okay. Well, now that you've heard the most interesting part of the tour today, far more interesting than anything John or I have to say, but we appreciate your attention. So I'm here to, in 20 minutes, create some awareness about a new initiative that we've started with the VSF back last October, I think is when we first started talking about it. Is that right, John? Something like that. So we're calling it the Cloud Device Discovery Initiative. So maybe before we get into this, Brian is not with me today, but he's the guy doing all the work, so I have to give him the credit. So about us as presenters, so my name's Sydney Lovely. I work for AWS Elemental. That's the AWS Media Services team within Amazon. Prior to that, I was head of engineering for 10 years at Grass Valley. And prior to that, I was with Harmonic in the media server business for 7 years. So been in the industry for just a minute. My colleague Brian's been with AWS Elemental for about 8 years, and prior to that, he was a software developer with Intel going back to the way back days. So a quick word about AWS Elemental. So we offer a range of media services, including Media Connect and Media Live. So Media Connect is the service that I run, which is, you can kind of think about it as the front door to the cloud. This is the way to get live signals into the cloud. Media Lives are live transcoders, so for all of your OTT delivery needs. All that goes on to packaging, tailor, and off to the consumer. And we also offer a file-based transcode service called Media Convert. So Media Connect use cases are kind of interesting because it's really been focused on getting your signals in and out of the cloud. So it kind of usually starts with going into a virtual private cloud. So these are the things where you'd be using things like Ansible and Terraform and things to set up your workflow in your environment. It's also focused on getting things cross-region to other regions in the world and cross-account. And the thing that's interesting about this is that lots and lots of customers we've talked to, they tell us that oftentimes, all of this stuff, and as hard and challenging as the Ansible and Terraform stuff is, you end up with getting signals into and out of the cloud in the first place is often the hardest challenge, they're telling us. So why is this? And if you think about it, there's lots of transport protocols out there to choose from that provide reliable transport into and out of the cloud. So protocols like RIST, SRT, even TR07. The challenge, though, is this really requires a sophisticated set of networking skills for most customers to manage that. So if you think about it, you have your on-prem network. It's usually behind a firewall with a set of private IP addresses. Those things hit the public internet, which NAT to public IP addresses. Oftentimes they're leased and they change over time. And then that's to the security group, which is sort of the firewall within the cloud. Moving on to finally getting into your virtual private cloud. So this is not something that a typical camera technician is going to be able to deal with. The good news is, though, this isn't a unique problem. It's unique to maybe our industry. It's not unique to the IT industry. So the IT industry has dealt with this for a long time with something called IoT technologies. So this is the ability to find and discover devices and securely and reliably pair them to the cloud. So back in October and then end up at VSF in February, we've started a new activity group based on cloud device discovery. So this whole thing contemplates essentially a new technical recommendation that's currently in an activity group within the VSF, along with an open source SDK and a reference design service. So the idea here is that I think we've learned our lesson over time in the industry that things that come with open source SDKs are easy to integrate, easy to adopt, and so that's a key part of what we're offering here. So some of the issues that you have with current workflows, in addition to just connecting and the network issues, there's a lot of manual connectivity required to be able to do the record keeping track of all your devices in the wild, all their IP addresses, accessing things remotely through VPC tunneling, configuration, and then persistent monitoring. And it reminds me a lot of the days in 2110 and 2022-6 before we had things like NMOS, right? We were manually managing large multicast IP addresses in spreadsheets and those types of things. There is a better way. So the idea with the CDD SDK is it provides several key benefits. So first of all, the idea is that you can essentially push a button on your device, as long as it has the SDK in it. It will connect to a service. It doesn't have to be an AWS service. There's nothing Amazon specific about this. It could be in Google. It could be in a private data center. But the cool thing is you don't actually have to deal with any IP addresses whatsoever. It registers with the backend service, and you can pair it with a pairing code like you would with your Netflix account. From there, once you have a secure connection to the device, again, not a transport connection for video, but a communication and control connection that allows you to automatically connect and set up all the network settings all in software, manage the connections persistently, and then monitor it 24/7. So for example, we have a customer that's interested in using a whole bunch of small encoders to monitor traffic cameras in a city. And these things are up on poles. They're not something you can, you have to roll a truck to go change an IP address on that. So the ability to remotely connect to that and control it and manage it from the cloud is critical in those types of applications. So this was a demo. We're going to skip past that in the interest of time. But we have, I guess, getting into a little bit more in the details here. I don't know how much time I have left. But the CDD ultimately starts with an SDK. This SDK is transport agnostic, so it rides alongside of what you would do with RIST or with SRT or with TR07. So it can run on any devices that are connected to the cloud. That could be a camera, an encoder, a decoder, etc. The client device launches an SDK and then basically communicates with your service wherever it's running. That SDK then ends up ultimately setting up a secure MQTT connection, which is a protocol used by IoT. And then the schema between the cloud and the devices is a fixed schema that defines all the typical things you typically need for connection management. So things like bitrate, codec, and so on. But it's also an extensible schema. So if you want to be able to use the API in the cloud to directly control devices and do things like change graphics layers on a graphics engine, for example, you can do that and build on top of the schema. A little bit more detail on the technology here. So again, initially, you're behind a firewall. Your SDK is running on something. right? It communicates through HTTP initially to the cloud, but then ultimately sets up that MQTT connection. And again, one of the nice things about this is there's no, calling up the IT department, punch a hole in my firewall. It's all using well accepted principles. So I'm going to skip forward a little bit here in the interest of time, past some of the little more nitty gritty on how things work. And talk a little bit more about kind of where we go from here. So kind of what's available now. So currently available as of, I think, probably April. We have an actual SDK available that's been under review with the activity group within the VSF now for several months. That's available on GitHub, so you can download it. It comes with a reference design that basically mocks a video endpoint using FFmpeg that you can run on a computer. We also have CloudFormation templates, which is our version of Ansible and Terraform, that allows you to spin something up in Amazon that will communicate with that. And then the CDD communication protocol will, is obviously published, and there's a set of documentation alongside that. We've also started integration with multiple different vendors. And so we actually have an integration already with Osprey Video. So they have a small encoder device. They actually have a whole portfolio of products, but we've started with their small encoder. That small encoder is running the SDK and it's starting to get evaluated by broadcasters today. So, this is an open activity group in the industry. So we'd like to kind of get the activity group to kind of finalize the TR spec by, say, the end of the year. So there is a bi-weekly working CDD group that several folks are involved in. And again, the open source SDK is actively being developed and updated by multiple people. The cloud endpoint's developed, and Osprey, as I mentioned, has this operational today. So again, working towards finalizing the production version of the SDK, finalizing the communication protocol, and at that point, once that's been accepted and the VSF and folks that have been steering it are happy with that, we'll actually implement that within the Media Connect service at AWS as well. So this hopefully will help our customers move their workloads to the cloud more easily and help people take advantage of that next level of technology with minimizing some of the learning curve and the networking skills for everybody involved. And I think that's it. So, well, thank you.
Sydney, you got us all caught up.
Did I? Okay.
20 minutes left, so if we have any questions, we're happy to take those with John or Sydney. Otherwise, you're welcome to just relax. If you guys would like more coffee or anything, please let us know. And you can enjoy the rest of the cruise. This is one of my little favorite coves here. There's always birds on that log. Doesn't matter what time you go by, but there's always birds on that log, and they've been different birds all day long.
Even when it's raining.
I know. They're always there.
Did it rain today at all?
It did not. We had beautiful weather today. Yeah, we were very, very lucky based on the last couple days. And just so everyone knows, these presentations will be available on, because we scanned your badge, you will get an email as soon as they're up, and so you're welcome to download them.
All right.